Huh? It depends. Okay, overcurrent protection device. So what we picked, guys, we picked for you a couple of things about overcurrent protection device. When it comes to overcurrent protection devices, um, I don't know how many of you guys have dealt with higher than 600 volt. If you deal with higher than 600 volt, you know that overcurrent protection is only one function that will protect the power system from. There's over under frequency, over under voltage, directional current, um, open phasing on certain equipment. So there's many aspects that a power system need to be protected from. The notoriously famous, the easiest way of protection is from overcurrent. So overcurrent, like we said, there are three conditions for overcurrent. Condition number one, you grab phase A, phase B, phase C from, say if you have phase A, B, and C on a number 12 THR conductor, with a wire knot tied together, put a wire knot here and flip the 20 amp multi-wire branch circuit, 20 amp, 3-pole circuit breaker on. That's your short circuit. That's the highest amount of short circuit they're going to encounter from phase A to B to C. The second one would be ground fault, like we talked about. You grab a phase A and bolt it to the frame of the enclosure. That would be a ground fault. That's a second. And the last one is the overcurrent protection device will provide you is overload. So your circuit is rated for 20 amps, and you keep adding each one of these fixtures, say it's 1 amp, keep adding to, you added 25 fixtures, and each one of them supposed to be 20 amps. So you put 25 amp load on a 20 amp circuit breaker. That's called an overload. So three conditions constitute overcurrent: overload, ground fault, and short circuit. That's very, very important to understand that one. Overcurrent protection device is a big deal. So what we did for you, I don't know how many of you have seen the selective protective devices from Cooper Busman. Have you guys seen this one? Do you guys use fuses a lot? If you use fuses a lot, this is must-have. It's in a PDF format. You'll see me flashing it a couple of times later on. It walks you through a couple of coordination for fuses, and if you're like me, you get confused between there's hundreds of types of fuses and applications that will guide you through the mess of overcurrent protection device using fuses. So really good to have. There's also the handbook for electrical safety. Jeff teaches 70 and I teach 70. When we do 70, that will tell you what type of PPE you need to work on the electrical equipment safe. So that's directly tied to the size and the settings of the overcurrent protection device. So it's a big deal. And of course 70E, you guys are familiar with 70E and the arc flash, arc blast, shock hazard, and arc flash hazard that can come from any power system. The arc flash, arc blast is directly proportional to the amount of short circuit that your power system can inject into your building. So when we talk about protection device, it's directly related to the proper PPE that you will gear up when you work energized on electrical equipment. So big deal. 70E. A couple of things, guys, I always like to share with you. Now, I'm an engineer, so I love books. So if it scares you guys, I'm up to 800 technical books in my own library at home. So I even brought my engineering books from the motherland in Jerusalem all the way here to Bloomington, so I can have them next to me. So what I did, they have a practical solution guide for arc flash hazard. You guys can download this one if you're interested. Free. These are free. Practical solution. I like the word practical, especially for a lot of electricians. This is Easy Power, a company that does short circuit analysis software. A bunch of engineers and technicians got together and wrote a practical solution. So I read half of it. I just got it a couple of months ago. So if anybody's interested, drop me an email, and I'll share my email with you. It's really cool about arc flash hazard. So that's a really good one. When it comes to also overcurrent protection device, guys, I don't know, all of you have the white book, 2012 now. the white book. When I teach, when we go into safety and maintenance, you guys do maintenance. How many of you do maintenance? Electrical maintenance, electrical equipment. You do a lot of maintenance, electrical equipment. There's when we do maintenance electrical equipment, I always say the safety of the electrical power system starts with installing safe equipment. So how do you make sure that this 4,000 amp switch gear, 85,000 amp interrupting withstand rating, is really going to interrupt an 85,000 switch short circuit? How do you know that what's written on this piece of equipment is what the piece of equipment is going to act? Well, I don't know. I don't have an current injector to put 85,000 amp into an 85,000 withstand switch gear to check it. So what we depend on, like you guys are familiar with, UL listing. So when I see UL list on the switch gear, at least I feel comfortable as an engineer and electrician to design and install this piece of equipment. So safety starts with safe equipment to install. We use UL for this. Then now we install, we have a safe equipment. When we design it, guys, the next step, so first step is safe equipment right here. That will tell you the safe equipment, because UL test them to a certain standard. The second one, when we design and install it, we have to install it based on safety too. So that will come installing the safe equipment in a safe designing it safely and installing it safely. That will come 2011, right? And NEC 2011. When we design a power system, we design it based on NEC code because we believe the NEC code book is the minimum safety design and installation standard. Cool. Now we design it and install it safely. The next becomes, I don't know how many of you guys have this one. This is NFPA 70B. 70B, anybody here ever heard of NFPA 70B? I don't know if you did. Anybody else? 70B. 70B, it says recommended practice for electrical maintenance. If you have a piece of equipment, guys, it's very, very good piece of equipment when you install it. Do you think the same piece of equipment is going to act the same way 10 years from the day of installation? Absolutely not. If you think your circuit breaker that you installed in 1990 is going to trip based on the same tripping function in 2013, you're wrong. Because over time, they're going to age, dirt, use and abuse over time. So that's where electrical equipment maintenance become deal. For a safe electrical power to continue being safe, you have to maintain that electrical equipment. This document will walk you through how to safely maintain electrical equipment and develop something what we call a preventative electrical maintenance program in your building, especially if you're dealing with hospitals, sport arenas, and bigger buildings. So you develop an electrical preventative maintenance program that you implement into your plan to continue to make sure that your equipment is safe. And of course, the last one on the puzzle is the NEC 70E. 70E will tell you, as you maintain your equipment to continue the integrity of these equipment for years to come. By the way, when you install a power system, you're looking at 40 to 50 years of life with good maintenance, right? At least 50 years. So some of us, when we design a building, we might not live enough to see the end of that building. You know, if we design it today, 50 years from now, I don't think I'll be around 50 years from now. So for 50 years to work on these equipment safely, you have to 70E. Work energize. Energize or shock hazard. Work energize, you got your 70. So between all these documents, you guys got yourself a safe electrical system, equipment safe, design and installed safe, maintained for safety, and as you maintain it, work on it with safety in mind by putting your PPE, either lock out, tag out, you lock it, you tag it, put it in a safe working operating condition, right? So safe, lock it, tag it, and go through the procedure of locking and tagging. Work on it, energize, that's a rule. The exception is when you work on it, energize, and when you work on it, energize, you have to assess the hazard and go through the whole hazard assessment, and then put your PPE and start working on it. So that's, with all this, having said this, the major factor on protecting you, especially from the hazard, the shock hazard, as well as the arc flash hazard, is the overcurrent protection devices in your power system. That's it. without the overcurrent protection devices, your switch gear is nothing but a bunch of wire nuts, basically, and bolts and so forth. It would not protect you from anything in any shape or form. So that's why we picked guys, the NEC code book, the 240, which is overcurrent protection device. This is a disclaimer that if I give you an advice and you go back and take it, and you burn your building, you remember Suamiya? Did you tell them just that one? You don't say the engineer had told me that. So a couple of things, and equipment approval requirement. We'll talk about this one. Overcurrent protection device terms and definitions and basic overcurrent protection installation. When I'm going through this, I'll be showing you guys the software that I use as an engineer, how to do overcurrent protection coordination, and show you a couple of things that the engineers do. And if you work in high-profile jobs, you most likely have seen the overcurrent protection coordination terms and sheets that you get. So 70 most widely used, we talk about this one. This is very important, guys. 90.7. Equipment has been listed by qualified electrical testing laboratory. Gentlemen, you're looking at it, and ladies, you're looking at it right here. That is recognized. It shall be suitable for installation in according to the NEC code book. So you've got a switch gear from China. No, you are listing on it. You are not to design it, install it in your building. The only option you have, you got from China, from anywhere you want. The option that we have right now in Minnesota is you hire, there's a bunch of engineers in Minnesota listed with the Department of Labor Industry as recognized by the department that can give you a signature or a report about a piece of equipment made in China that's not UL listed, that when you get that report from the engineer, it's equivalent to a UL listing. There's a bunch of engineers who do that. It's really scary. You know, I'm not one of them. So, but you can hire an engineer basically if you have the equipment. Yes, sir.
Very quickly, if you had a situation like that in a hospital, so the hospital bought something from some other country, Australia, and they brought it in and actually built it on site, and the inspector came in and said, you know, all these pieces were with this device are not listed, you need to do something else here. And so that was applicable. They had come out, inspectors, they prove it.
An engineer.
Right.
Yeah.
So the state had to come and say it.
Absolutely. Absolutely. So that's alternative, and it's closer than you think, guys, because we buy equipment from all over the world, and these equipment could be, most of the manufactured equipment are aware of UL listing and they list them. Some are not. So we have to get into finding an engineer or a third party to approve it. Okay, so these are the safe equipment. Now we have my safe equipment to install it. Then approval is acceptable to the authority having jurisdiction. So most of the inspectors are smart enough to know what they know and know what they don't know. So if they see a UL list on a switch gear, they're smart enough to say, well, who am I to disagree with UL? Can you? Do you guys have enough? I mean, if UL says this switch gear can handle 85,000 amps, and I'm willing to put my NIC as a UL on it, can you say no? I mean, as I don't feel comfortable as an engineer registered, you need to say no. You know, I don't have the equipment to test them. So the authority having jurisdiction, typically, if you have a third-party verification acceptable, they will accept it. Otherwise, you have to go to a list of engineers to get you the approval. Just because of the equipment, there is examination, verification, installation of equipment. This is a big deal. Installation, use, listed or labeled equipment have to be installed and used in accordance with any instruction included in the listing or labeling. I had this situation, Jeff, we talked about this one. GFCI receptacles in an accessible location. Did you guys hear about that one? Has to be in an accessible location as of 2011. Right? Accessible location. So take this scenario. Now, if you have a GFCI, and if you look where the GFCI accessible location is located, if you have a GFCI that are powering a vending machine, does it have to be in an accessible location? Well, most of the people will say no, because the accessibility is related to most of the GFCI installed in dwelling and non-dwelling location. 6 feet from a sink, countertop in a kitchen, all this, these have to be accessible. Now, if it's feeding a fountain, for example, fountain has to be plugged into GFCI, or if it's feeding, or if it's powering vending machine, if you read it literally, it doesn't have to be, but look at the listing. They had this discussion with Sam there. Listing, if you look at the listing of the GFCI, it has to be exercised monthly, right? So now, by interpretation, some inspector will come. If it has to be tested monthly, how are you going to move this plasma TV or this big vending machine to test that device, right? It's not accessible. So that's why they catch you a lot on equipment, though the code doesn't say certain things, but based on listing and labeling, installing certain equipment based on the NEC code might violate the listing and labeling for them. Another very good example, which we don't do, you take this fixture right here and install it in the parking lot. It's listed and labeled, right? But not for outdoor wet location. So that's what becomes listing and labeling become big deal. It has to be listed and labeled. It has to be used based on the listing and labeling for equipment. These are a bunch of things that Jeff and his group at MEA put together. These are testing agencies recognized by OSHA. I don't know how many of you guys have dealt with this. I dealt with Factory Mutual. Anybody dealt with Factory Mutual? FM. Factory Mutual. I don't know if you guys have dealt with that one. At one time, it used to be, and we still, we're environmentally friendly people. So if you want to install a transformer in your building and you need a biodegradable oil instead of mineral oil, environmentally friendly, no spill, nothing, less hazard in terms of arcing and so forth. So when we install it, a lot of owners or building owners, they want to be environmentally friendly, so they want biodegradable transformers. And to get you biodegradable transformer listing, we used to put FM, Factory Mutual label on it. That's an environmentally friendly transformer, which is basically biodegradable, almost olive oil that you can put in that transformer. So that's how I dealt with that one. A couple of others, guys. Here's a bunch of others that you deal with. I'm going to go right through all this. Jump in if any. Of course, UL is in the commercially famous one of them. With the book that we said, this is 2008. I believe 2012. How many of you guys have seen this book? Have you seen this book? The nice thing about this book, and I really got introduced to it lately, not many years. If you want to know what is the UL listing for a switchboard versus a switchboard, okay, that's too much. How about a panel board versus a load center? We deal with panel board load centers all the time. What's the listing for them and what's the description for all of them? So what they did, those guys, they took the NEC code book articles and they relabeled them. So if you're looking at you took all the articles from the NEC code book right here, and they put them in a table and assigned to every one of these articles a UL listing. So if you're looking at a switch gear, you come over here and you go to the location where your switch gear or panel, whatever is located, and it will tell you what is the UL listing of this piece of equipment. So it's really cool, make it almost very, very user-friendly. So for example, I'm picking, there's resistors and reactors. Resistors and reactors, UL product category code for resistor and reactors is it's in the code, it's 470.1 in the NEC code book. It's NMTR, and they give you a table, a page number, where in this book you can find this, you can read more about it. So what I'm trying to get to is they make it very, very easy. If you know the equipment in the NEC code book, that's all what you need. I want to know load center, right? From the NEC code book, you can go to the to the white book and find the labeling, the UL labeling. Or you can contact UL and they'll give you a lot of information. They're more than happy to help you do. So all those guys are acceptable and approved methods of getting into energized equipment. So I'm going to move fast to all this and get you back into. So why all this stuff, guys? Because of you cannot have a safely designed and constructed electrical system if your equipment that you're constructing and installing are not safe. Right? It defeats the purpose. You can't make this picture, design it safe and install it safe if it's not made safe. Safety starts with the equipment that you install. Terms and definitions. So that's A couple of things, guys, about definition since we're talking about overcurrent protection device. This is how they define it. Over a branch circuit overcurrent. And what bugs me about it, it's one thing I'm going to tell you here. When you read branch circuit overcurrent protection device, what does come to your mind as masters in journeyman? When you hear branch circuit, it's a branch circuit. But if you look at the definition, a branch circuit can protect what? Service. So why do you call it branch circuit? It used to bug me all the time, and I still don't know why the word branch circuit over. Why don't say overcurrent protection device here? Because branch circuit overcurrent protection device capable of providing protection for service, so it's not just branch circuit, feeders and branch circuit, and over the full range from the rated amp to the interrupting range. So that's a major range. So what I'm going to bring to your attention, guys, in the electrical code, there are 3 circuits dear to your heart, and dear to my heart, and should be dear to your heart too. Circuit number 1 is the conductors coming from the utility transformer and dumping that power into your building. These are called service entrance conductors. That's circuit 1. We brought the power to the building, the first disconnect, the first service equipment. From the first disconnect service equipment, we dump that power, we distribute that power inside your building. Between panel A and panel B and C and D, these are called feeders. So here's the feeders, we protect them too. And the last one, from the 20 amp circuit breaker into that light, that's called your branch circuit. Or from the 400 amp into the air handling unit, or chillers that you have, that's your branch circuit. So these are very, very important. The code treat them differently, have different articles. I'm sure you guys are familiar with that one. So overcurrent protection device is supposed to protect all of them. Full range, so if you have a 20 amp circuit, it's supposed to protect you if you exceed 25 amps, all the way to the interrupting range. So if your 20 amp circuit breaker says 20 amp, put 25 in it, it will sit there for a couple of minutes and trip. If you put 5,000 amps out of it, that's short circuit. It will also trip very fast within typically 3 cycles. So that's from the full load all the way to the interrupting load. At 20 amp circuit, when it comes to overcurrent protection devices, guys, there are 2 amp ratings for them. One of them is the continuous, typically continuous operation of the amps. 20 amps is a 20 amp. The load operation, 20 amp is a 20 amp, pull 20 amp out of it. And the second one is the interrupting operation. Now, interrupting operation, if you short circuit, the circuit breaker has an interrupting operation rating, which is 10K, 10,000 amps. This circuit breaker can handle. If you put 11 in that circuit breaker, that could explode, or it could turn into a conductor, solidly bolt together, and it doesn't interrupt. So that definition is really, I thought, is really interesting. Branch circuit protected devices are provided with interrupting rating for the intended use, but not less than 5K. So 5K is your minimum on the interrupting. In the power system, typically a 20 amp circuit breaker has what's the interrupting rating on it? Minimum that you install it. 10K. They're all rated for 10K. 10K, meaning 10,000 amps. This circuit breaker is capable of interrupting before it turns into a big ball of fire. Big ball of fire. So that's your overcurrent protection device. I can't emphasize the word surface feeder and branch circuit, though the name says overcurrent branch circuit, but it protects all of them. Continuous operation. Continuous operation, I can't emphasize that it's a 3 hours or more, and the maximum current expected to continue for 3 hours or more. So, maximum current, so if you have a piece of equipment and an air handling unit, and the full load amp of this air handling unit is 50 amps. So when it's fully loaded, it's 50 amps. If that 50 amp continue for 3 hours or more, this piece of equipment is what? Continuous. Now what happens if we have a VFD on it and we're driving it lower and we drove it and we're pulling out of it because we're not driving it as much? We're pulling out of it, say, 25 amps out of 50 amps. We're not utilizing the full power of that device. Then based on the NEC code book, this is not continuous load, right? But we don't get into splitting here, guys. If the equipment can run continuously, we always assume it, and we don't. A lot of people don't pay attention to the word maximum here. We assume it's going to be the maximum for 3 hours or more, then it's continuous load. Who cares? If you were to pull continuous load out of a circuit breaker, that circuit breaker has to be derated to 80% of its full load rating. Example. 100 amp circuit breaker tied to a continuous load like this. You cannot pull continuously 3 hours or more out of this 100 amp more than 80% of 100, which is what? 80 amps. Exception is for so-called 100% rated circuit breakers. 100% rated circuit breakers, as the name indicated, is if this is 100 amps, it's 100 amps. Continuous or non-continuous. Typically, you start dealing with these if you have 1,000 or more. You can go down to 600 continuous duty or more, but typically start making sense at 1,000 amps or more at any voltages. This is just telling you about the continuous load. If you are to size the branch circuit supplying continuous load, look what you have to do. You have to have the overcurrent protection device shall not be less than the non-continuous load plus 125% of the continuous load. That's, I know a lot of, Jeff, you guys did, what did you do? Residential calculation yesterday, right?
Which one?
Yeah, you did residential calc yesterday? Okay. So we do a lot of, I do residential calc and commercial calculation. When you size a service for a building, that's how you size your service for your building. You take all your lights, multiply them by 1.25, assume continuous load, all your receptacles are non-continuous load, then you're going to add them at face value after you also derating. There's a derating factor that we do. So that's how we size your overcurrent protection device. So out of 100 amp circuit breaker, I can pull 80% continuous, 80 amps continuous, and the other 20% leftovers. They're not sitting there doing nothing. I can pull them as a non-continuous, right? So receptacles, they're energized. I took the 20 amps for 2 hours and then off, right? Not 3 hours. So, because some people think if it's 80% of the circuit breaker, this means the other 20 are doing nothing there. They are feeding the non-continuous load, but not, they turn them off. They don't continue to operate for more than 3 hours. So that's a big deal when it comes to sizing the overcurrent protection device. Overcurrent protection device supplying continuous loads for feeders too. So the first one here, guys, you can see that this is for branch circuit. And you see that, that's article for branch circuit. The same article is also for feeders. So same calculation, continuous 125%. So you take 125% on the continuous, add the non-continuous, size your overcurrent protection device. So that's when we size them. Any comments, guys, about sizing them? So a good example of that one is if you have just simple example, say if I have 100 amp load, this is this 100 amp is non-continuous right here, and a continuous, another 100 amp continuous, and I need to size the service for it. So you take the first 100, add to it 1.25 of multiply it by the second 100, right? That's the 25 extra on it, and your service size, my friend, and add them up, and if I did my math right, your service will be 225 amp. That's how this could be a branch circuit or a feeder or a service conductor. Any comments, guys? Any questions? So that's 225 amp you can pull out of this, the size of your panel. If that was, and this is the size an overcurrent protection device, what if that was not, what if I end up with 230? What do you do? What's the next standard? From 230 to 250. You go to the next standard. Okay, overcurrent protection devices, guys, are some of them are circuit breakers. There's adjustable circuit breakers, and there's instantaneous flip circuit breakers. The circuit breakers in general, they're devices that can manually grab it and use it as a switch, turn on and off. As a matter of fact, we use them sometimes as switches to turn things on and off with a manual. Well, that switch is cheaper to use. The reason why we have them is because under normal operating condition, you can use them as a switch. Under abnormal operating conditions, short circuit or ground fault, they will work automatically to trip if they reach their tripping value. That's what their job is. So without damaging to itself, when properly applied within its rating, very, very important. Automatically they will trip on a predetermined value to protect the system without exploding, right? Without exploding, dying in the process. So that's what the circuit breaker. There's adjustable. The circuit breakers, guys, are three types. I don't know how many of you guys were dealt with adjustable circuit breaker. There's fixed circuit breakers. What you see is what you get. And there's instantaneous trip circuit breakers, and there is adjustable circuit breakers. So I don't know if I can jump into here. So I have my okay, come on here. There you go. So here's my this is called Power Tools for Windows SKM. We use it to do a lot of calculation, guys. So let me see if I can get my curves here. Here's my cooling unit here. Okay, no changes. I just want to show you an adjustable circuit breaker. This is what the engineers do. Click on that one. This is a very typical adjustable circuit breaker. So here's a long time LTPU. How many of you guys set adjustable circuit breakers? Did you do sitting on adjustable? They give you a screwdriver, and you go in the face of circuit breaker, a couple of dials, dial them up. As you dial them up, be careful, because you are basically creating a newly designed circuit breaker. So one dial will say LTPU. This stands for long time pickup. That's your overload. So this one is set at 1 right now. I can reduce that boy. Now you're looking at, in this case, you're looking at 100 amp. You're looking at 800 amp frame. Adjustable circuit breaker. A frame, guys, is a box, a drawer. How big of a box you can fit. That's your frame. Inside this box, the maximum is 800. I stuck a sensor. These are your CTs, 400. I don't want to take the full 800. And then out inside the sensor, I can plug my circuit breaker into. So I take a frame of 800, sense at 400, because I don't care about the all 800. And I can plug it, a little plug on the face of circuit breaker down. Here's my options, 200, 250, 300, and 400. That's an adjustable circuit breaker. Every time you pick one of these settings, you have brand new circuit breaker. So I'm sitting it right now, and every time you pick a new plug, you see how many plugs I have? I have 200 all the way to 800. The maximum is 800. I can plug and sense the CTs that you put on them. Okay, now after I sense it here, now I have a 300 amp circuit breaker. If I set this one at, can you guys see the settings here? You can set it at 0.5. Now this 300 circuit breaker have turned into half of this, because I set it up at half, so that will be 150. I have just turned the circuit breaker just by tweaking the dial on it into a 150 circuit breaker. What they do here is they take the 0.5 setting multiplied by this. That'll give you 300 multiplied by 0.5. Now you got yourself, but just by dialing that thing, 150 circuit breaker. Very, very dangerous to mess with. The code require you, these dials, to be locked in, only accessible to qualified people, or you have to put them behind covers that covered and bolted, so people don't go accidentally start adjusting them as they move around, as they sweep the electrical room and go adjust the circuit breakers in between. Okay, so that's what you're looking at. That circuit breaker, long time pickup. That's the big component here. I want to go take this one back into my, see how easy that is? That one, you circuit breaker. Then you get into long time delay. Long time delay is that little deal here. Can you guys see that? That here. So this will, this is responsible for your arc flash value that's going to burn you if you have an arc flash incident. The higher than this number here, long time delay, you're telling the circuit breaker, if you have an arc flash incident right now, wait 7 minutes, 7 seconds at this value before you trip. So the lower the value here, the better arc flash protection, or the better chances of surviving an arc flash protection. That's your long time delay. How much I want to delay this process? Short time pickup, that's your short circuit right in here. Here's my short time pickup. Right now it's set if I can, this is my short time pickup right in this component here. So if I have a short circuit, at what value do I need the circuit breaker to trip? Right now I'm setting it at 6. So that would be 6 times this. 6 times 300 is what? 3 times 6 is what? At 1800 amp, I want this baby to trip. If you move it, look at 1800 amp. Now let me go screw it up more. Let's go put it at 10. Now when you put 10, we went from 1800 amp into what? 3000 amp, allowing more circuit breaker to sit in your system. Guys, all this will decide what the PPE that you need and what the category of the hazard that you're going to do. So that's an adjustable circuit breaker. Short time delay, I want that 3000 amp short circuit to sit on my system, look at that, for 0.5 seconds. It's eternity in terms of arc flash. I can change this one. Right here, you can adjust that one too. That's so I can go 0.4 to 0.1 of a second. Can you guys see how it adjusts the curves? The curves keep going. And the last one is, so this is for the short circuit. This one is long time, the short instantaneous. That one's called instantaneous. My instantaneous. If all hell break loose, and I have a bolted 3-phase short circuit, I want my circuit breaker to trip at, it's set at 12 now, so 12 times the pickup times this. So 12 times this number, that's when my short circuit, when my circuit breaker is going to wake up and start serving. 12 times 3. So that's how much short circuit, when it sees this, it will instantly trip. Instantly trip. So anyway, so you're looking at the circuit breaker, fan, yes sir. Instantly within 3 cycles. Yeah, within 3 cycles. So here's the, see, can you guys see that one here? That's, now I'm reducing it. You can, this is how you adjust these circuit breakers. To make it easy, how many of you guys have seen these? The nice thing when you do overcurrent coordination, when the engineers charge you an arm and leg for to do that, I don't know about you guys, it's hard to look at numbers and compare them together, harder to look at numbers than look at graphics. I can see if these two curves are not touching, I am fully coordinated. Versus, look at the settings for this curve and look at the setting for this curve. Can you tell from the settings if they're coordinated or not? The smarter than Chad made a lot of money by graphically representing the setting of your circuit breakers on a graphic interface here. And if they don't touch each other, I can easily tell they're coordinated. So that's what this is. So, and you can see the higher, here's my full-time pickup, this 300 amp, and this is my short circuit right here. It's looking at right here at 3000 almost. That's going to pick 3200. Now I can make it shorter. Can you guys see that? Now it's going to pick up but much less than that if I bring it this way. It's picking right now at almost 574. So that's what an adjustable circuit breaker is. Any comments, guys? Any questions? So this is my amps, picking up amps. This is the time. 0.1 of a second is right here, and the second, 10 seconds, all these are in seconds. Can you guys see instantaneously you're tripping within less than 0.08 or 0.07 right here. So within 3 cycles. That's the 3 cycles for the circuit breaker. 1 cycle, 2 cycles, 3 cycles, your circuit breaker should trip. Current limiting fuses, they trip within a quarter of a cycle. You can imagine how much you can, we'll talk about this one, how much energy you can reduce if you trip in a quarter of a cycle versus 3 cycles. Who cares? The amount of arc that's going to come out of the switch here, it's going to be completely different if it's 3 cycles than if it's a quarter of a cycle or a half a cycle. What's a cycle in terms of time? A cycle is 1 over 60. So it's 3 cycles, 3 over 60 of a second. That'll give you 1/20th of a second. Because we measure the action of circuit breakers are measured in cycles because we need a smaller unit to measure with. So you call it a cycle, but a cycle is 1/60th of a second. 3 cycles is 1/20th of a second. Any comments, guys, about adjustable circuit breakers? So this is fully adjustable electronic circuit breakers. This device is actually Cutler hammer. I like Cutler hammer. DS2, the name of the catalog number, RMS 510, 6, all the 5 series here and the 8 series. The only difference between the series is how much intelligent the device is. So it's a Cutler hammer DS. Anybody dealt with Cutler hammer? That's their electronic adjustable circuit breaker. Now let's go to that one. Is kind of a dumber than a rock circuit breaker here. This guy is, this is a fixed circuit breaker. Can you see that? The only thing I can adjust is this side is fixed right in here. The only thing I can adjust is the instantaneous. why would they make all these circuit breakers different sizes? The fully adjustable circuit breakers, you're looking at probably at least 5 times more expensive than the fixed circuit breakers. So if you can see, this is 70 amp circuit breaker. I can trip, depending on the series. If I say 70 here, the thermal curve is fixed. I can't adjust it in any way, shape, or form. The top here, the instantaneous I can. Can you guys see the instantaneous here? I can adjust my instantaneous right here. That's the only time I can adjust it. So I can have a low here or a high here. These are the only two options. Where would you use a circuit breaker like this? Air handling unit, chillers, motors, rooftop units. If you have a circuit breaker that's protecting motors, anything that has a motors or compressors in it, you need the cheapest circuit breaker to install. You need a fixed circuit breaker with an adjustable instantaneous. And as you guys know, we use the adjustable instantaneous because of the air rush of these motors. So they allow us to adjust the instantaneous to avoid nuisance tripping when these equipment energize because of their air rush. But still cheap. So you're looking at a fixed circuit breaker with an adjustable instantaneous one, and the second boy here is fully electronically adjustable circuit breaker. And guys, all these are recognized in the NEC code book. I don't think it's the only engineers. This is 240.6a is the fixed and B is the adjustable. So these are all in the NEC code book. Any comments, guys? Any questions about that? Adjustable versus fixed? So that's what I like to show you on that one. So here's my adjustable circuit breakers, and you can determine instantaneous tripping. I should have showed you the instantaneous. The instantaneous came here, right here. Can you guys see that leg here where it says instantaneous? That one here. This is this leg here is called instantaneous. Let me show you what happened if the circuit breaker does not have instantaneous. So if you delete this instantaneous, which never do, because you're going to burn your equipment. Okay, where are we here? Okay, so delete segment. See what happened here? What happened to this curve? Went up. Now the short circuit is going to sit in your system 0.1, 0.2, 0.3, 0.4, 0.5 of a second. Right? 0.5 of a second. 0.5 of a second, guys, is half a second. Half a second is eternity. Enough to burn your equipment completely. If your equipment is not rated for ARC equipment, they call them, or draw out ANSI rated switchgear. Unless you have an ANSI draw out or ANSI rated switchgear, and you do this in your circuit breaker, you have just burned your equipment. So that's what the instantaneous circuit breaker is. That piece here is my instantaneous. So the smarter than Chad, they designed a circuit breaker, believe it or not, just have this little leg and call it instantaneous circuit breaker. That's it. No long time pickup, no short time pickup, no long time pickup, no short time pickup, no long time delay, no short time delay. The only thing I'm interested in is the instantaneous. Collar Hammer called them motor protectors. Anybody have seen them? It's called motor protectors. They are sized in short circuit. When you buy them as sitting A will give you 5,000 amp. They look like a circuit breaker, but the brain inside it is only looking at a short circuit. So it doesn't matter what happened here. We don't care. We're only looking at this section. They call them instantaneous trip circuit breakers. Who cares? They make cheaper equipment. Cheaper equipment. And what they do is they use them in conjunction on motors with overload. So here's your overload here. You guys talked about overload yesterday, and here's your instantaneous circuit breaker here. The instantaneous breaker will protect you from short circuit, and what do you think the overload is going to do? Protect you from overload. So between the two together, in conjunction, they will make a big, fat, good boy like this. So that's your instantaneous strip looking at the short circuit breakers. Have you ever guys thought about these curves when you came in? You thought that the NEC code book just applies to the fixed circuit breakers. And so when you go to 240.6b in particular, pay a lot of attention to adjustable circuit breakers. They adjust the time and the current or both. So that's your adjustable circuit breakers. Inverse type circuit breakers, we're just looking at, guys, and non-adjustable circuit breakers and adjustable circuit breaker settings. All these, I like to flash directly these, my curves, because it shows them, you can't show them better than that. So when you have a circuit breaker like this, let's go to the worst. So you can adjust all the amps. You can adjust the time here that you trip. Fixed circuit breaker, like I said, here's the fixed circuit breaker. The only setting that you can do is here. So these are the fixed circuit breaker adjustable. Time inverse. I want you guys to look at this one. The higher, look at how the curve goes. Can you guys see that curve? The higher the amps here, the faster the circuit breaker will trip. So if I'm sitting here, look how it goes faster. So if I go the short circuit at this value, it goes faster. If you go in the black, if you hit this leg here, all hell break loose and the circuit breaker will trip instantly. If you're coming at this value here, which is like, it looks like 21 right here, it's almost 20. Oh, the amps here are 900 amps, 400 amps, 0.9, like 400 amps. If you go all the way up to here, you're going to trip in 10, 11, 20 seconds. 20 seconds. So that's what the concept of inverse type circuit breaker. Higher amps, faster tripping, more protection. Faster tripping, more protection. Any comments, guys? Any questions about that? Circuit breakers? Did you guys eat a lot? Is that why you're so quiet now? Like I did? You saw about the setting of a circuit breaker, all these adjustments that you can do. Non-adjustable circuit breaker is what you see is what you get, you can't adjust it. Coordinated or selective. When you have overcurrent protection, coordination, or electrical selectivity, if you're working on the balance of this fixture and accidentally, you're not supposed to work hot on this, but say you worked on it hot and you shorted line to ground and the voltage here is 120 or 277. Do you want the 20 amp circuit breaker protecting the slide to trip or the 1200 amp main panel to trip? 20. 100 to 1200 amp trips. You have a bad day, right? Really bad day. So that's what the overcurrent protection device is. Assure you that if you have a short circuit or ground fault in one section of your power system, that particular section is the only one that will be outage, will be an outage in it, will be disconnected. Everything else will continue to operate properly. Required for hospitals, required for a lot of places that all the engineering projects that we did must have an overcurrent protection coordination. I'll show you this in a second. This is how it looks, the overcurrent protection devices. I like to show you the example that I have in mind because I just did it. It has more stuff on it too. Let me go back into my circuit breaker here. So closing that one. Okay, let me go show you a coordination. I have an air handling unit here. You guys are familiar with air handling unit, right? My air handling unit, and my air handling unit, there's a lot of information on it here. The start curve, let me go here, sitting. Okay, so I have the main that feeds the whole building. Let's look at the, I don't know if the one line diagram, okay, here you go. Can you guys see, this is the air handling circuit breaker right here. It's protecting the air handling unit right here, and right above, you're not seeing it here, right above it is the switch gear that feed the air handling unit. Cool? And you need to coordinate between the overcurrent protection device that feed the whole building with the circuit breaker that feed the air handling unit. So here's my, first of all, you need to do is you need to, the setting here, here's my main circuit breaker. I have a 400 amp circuit breaker to protect my air handling unit, adjustable one. Here's let me go see the curve. Can you guys see the curve, the starting curve of the air handling unit right here? So I am fully coordinated between this curve and this curve, little curve. And this is my overload. Let me see if I can set my overload. No, this one here. This is class 10 overload. Yesterday we talked about class 10 guys overload with Gary, with my friend Jeff. So here you can coordinate also with your overload and set your full load amp for your overload and make sure it's going to be protecting your equipment. So I can adjust this one here to 100 and shift and redraw, and it will move my full load amp to the overload factor is 1 now, so that my overload is going to protect the trip right now at 100. So in a case like so between the circuit breaker right here and the overload right here will provide a full protection for I know I have a lot of stuff on my equipment here. It will provide a full protection for the chiller or the air handling unit, which is right here. So that's what coordination. There's I did coordination also with a 20 amp circuit breaker. Here's my 20 amp circuit breaker. So I have a 20 amp circuit breaker right in here. If I have a short circuit in this area, this 20 right in this panel, this circuit breaker should trip before the main, which should be right here. It trips. So that circuit breaker is just for the lighting. This circuit breaker right here will allow your chiller to run and run, and if you have a short circuit on it, it will trip. So let me see if I can have the curve. Here's my circuit breaker is sitting at 208, 100 amp, 208 system. That's my circuit breaker curve. The full load amp for this one is 250, so 254. So if I want to go set my overload here, I'm not setting it right. If I set my overload to 200, what did you say, 250? 254 amp, and redraw. Can you guys see? Here's my overload now. It's kind of, so if you overload it more than this amps, you can multiply by 1.15 like you guys do, or 1.25. I did not do that, but sitting right here. This part is an overload backup. So if your overload is not to work for whatever reason, the circuit breaker, if it's set up this way, will act as a backup for your overload. So that's a couple of coordination. Let me see if I have a curve. Okay, here's receptacle lighting panel. Okay, here you go. So here's let me see if I can have a setting here out of here. 400 amp, trying to do a 225 amp panel. If I have can you guys see, here's a miscoordination where I have a 400 amp overlapping with a 225 amp panel based on the circuit breaker. Can you guys see right in here? I have a 225 amp panel and a 400 amp panel. They're not coordinating. They're overlapping. So what you need to do, you need to go adjust this one, because of a circuit breaker that it looks like it can't even do a whole lot. So you might have to use a different type of circuit breaker. So these two circuit breaker, they're not touching each other. Very clearly they're coordinating. The only time they're not coordinating is at the bottom here, which is when all hell break loose and you have a short circuit. At any other level other than three-phase short circuit, they're coordinating. This is a good coordination here, acceptable. The only thing that's not acceptable is at that level. And the only thing you can change it right now is by changing the type of the circuit breaker to make it coordinate, or the size. Any comments, guys? Any questions about overcurrent protection coordination? These nice looking graphic as visual representation of the settings that you do for the circuit breakers. So moving into back into, and that's the same thing that we have in here. Now these two curves are not touching each other at all. The only time that these two will raise and it will trip if you're right here. Now why wouldn't I care about this? This, just to give you an idea, I can draw here easily. This area here, guys, only represent right here where they overlap and there's miscoordination here. That in this area, that's only what did they say? Only 15% of the time when you have a solid three-phase. So 15% of the time, if you have a solid three-phase, you might not coordinate here. For 85% of the time, you have what? Ground faults, and you're fully coordinated. And that's as good as you can get on a system like this. Thank you, Jeff. We'll see you. On a system like this, that's as good as you can get when you coordinate um, a 90 amp circuit breaker with a 400 amp circuit breaker. That's as good as you can get. That's an acceptable coordination. So it's a risk that you can have. Yes, sir.
What if you're using fuses? How do you
Now, if you're using fuses, it will give you a better coordination. You can see if you look at some fuses, they're sharper in their cut, so they give you a better coordination. Fuses give you, depending on what type of fuses you use and you coordinate, will give you a better coordination. But they have a drawback on the fuses too. Single phasing situations, and you know they're not adjustable, they're replaceable. But this is an acceptable level of coordination. To get a full coordination, guys, you almost always have to go to an adjustable circuit breaker. Fully adjustable. But that will cover you unless the only time this will trip, if you have a sub panel right next to the main panel in the same room, and you went inside the panel on the load side of a 20 amp circuit breaker, 3-pole 20 amp circuit breaker, and you tied the load side phase A, phase B, phase C together with a wire and a wire nut, and flip that switch. You could trip the main. How often do you do that? How often does this happen? Could it happen? Yes. But how often does it happen? Not a whole lot. So that's why a lot of us, there's an acceptable level at the very high short circuit current. It could take the main with you. But other than that, is unacceptable. Here's a chart. If you don't have the fancy curves that Chad has, here's the rule that we use, guys, as engineers when we coordinate. If your feeder, for fuses, rule of thumb, if your feeder is half of your main, you have good coordination for fuses, typically. What does that mean? You have a fuse here, you have a fuse disconnect right here on the main, and you feed that panel, and you came out of here. The largest fuse that you're going to feed right in this area, say if this was a 100 amp fuse, the largest fuse that you should pull out of here is what? 50 amp. So the ratio is 2 to 1. Right? The main is twice as a feeder. Look at these. Almost most of them, if you use the same type of fuse, you have a good coordination. But the proper way of doing it, obviously, is to look at the curves. The proper way is to look at the curves, like I showed you, are they coordinated or not. So that's a rule of thumb. The rule of thumb for circuit breakers, I used to say 50, but to get a better coordination, probably a fourth. So if that was a circuit breaker, to get a good coordination, if that was 100 amp, then typically this is 100 amp. Here's circuit breaker coming in here, circuit breaker coming out. So 25 amp. That will give you a good coordination. If your feeder is 100 amp, the maximum that you can pull with a good coordination without worrying about it is 25 amps.
And how far do you take that? All the way down to the smallest?
Well, all what you're concerned about is now I'm taking a feeder here, okay, and I'm going to tab it. Now this have to be half of this. So let's just say it's fuse. If that was a fuse right here, disconnect, so this will be half of this. 50 will be what? 25 here. Do you see what I mean? And you keep going all the way down. Does that make sense? So the largest, the one from the largest. Then you take that one, half of that, all the way through. Yes, sir.
So like 100 amp, just an example of where that doesn't work in the windows, like a 100 amp panel in the house, 60 amp breaker for a sub panel. That's not 2 to 1, so automatically,
if you have
coordination here, just only for 100
even in your house. But remember, that's only for the 15%. Where you have miscoordination. The 15%, the ground faults, you're fully coordinated. But for the 15% that high, that's when you go to the sub panel in your garage. You grab that 60 amp load side, you tie with number 8 wire, tie the hot to the hot and flip the switch. Do you do that? Now that will trip your main too. You know what I mean? That's what we're talking about. You're good for coordination in terms of 85% for the ground fault. But that 15% become critical for a lot of applications. So 25, depending if you use the circuit breaker, some manufacturer can go also like match this to the fuse. You can go as high as 50 if you're using the same type of fuse, QO. You can go almost up to half of this like a fuse, and you still have an acceptable coordination. So in a 100 amp panel, you can have a 50 amp fuse and have an acceptable coordination. Rule of thumb. Otherwise, in an engineering project, guys, what we do is we pull all this data about the fuses, we coordinate them, and we do the best that we can do. On the 85%, you're almost guaranteed to if you keep these ratios. The 15%, you do the best that you can do at the bottom, knowing that highly unlikely that nobody's going to tie phase A to BTC and flip this much. So that's your overcomputation coordination and survivability of your system. This is talking about the fuses, low peak fuses, guys. Busman has a really good manual about low peak fuses. Now, when it comes to overcomputation devices, there are two reasons why you have them. Number one, if you have a short circuit or a ground fault or overload, you want them to trip. That every overcomputation device must do that. The second reason that we use them as to limit the energy. If you have a ground fault or a short circuit, do I want to limit the amount of energy coming? Meaning, do I want to burn all the switch gear? If I have a short circuit, half of the switch gear, do I want the PP? If somebody's working right here, do I want him or her to wear category 4 PPE or category 2? Both of them are acceptable in the NEC code book. But if you care about what category that guy or gal who are working right here is going to wear, then you get into low peak current limit fuses. Low peak current limit fuses. These guys not only trip to protect you from overload and short circuit and ground fault. That's must by code. But also, they trip fast enough that will limit the amount of heat that will be generated because of a short circuit and magnetic force that will be generated because of a short circuit. When you have a short circuit condition, guys, you have two forces working on that. One force is called shaking and baking. I call it shaking and baking. So the heat generated will shake. The heat will bake your switch gear. You're being tons of heat there. You're baking that piece of equipment. Okay, that's the heat generated from the short circuit. Also, the short circuit will generate magnetic force that shake that switch gear. So you have a piece of equipment that being shaken and baken by this current. How much shaking and baking will depend how fast Mr. Fuse or circuit breaker will trip. That guy will trip within a quarter of a cycle, like you can see here. The circuit breaker, and that's where the fuse guys become a big deal. The circuit breaker guys will trip within 3 cycles. Here's one cycle, and they will go up. Here's another cycle, and here's a third cycle. So imagine, a circuit breaker will wait up to this point to trip, versus a fuse will trip half of this one right here. Can you guys see the difference? Who cares? This means that much energy is going to be baking and shaking your switch gear, or that much energy. So that's when you get into the current limit fuses. There is two types of protection. Type 1, they call it type 1 protection. Type 1 protection means if you have a short circuit condition and you're properly dressed up to it, you will not die when you're working on it, number one. The circuit breaker will interrupt the circuit, but the circuit breaker might die in the process, meaning the circuit breaker will interrupt the circuit, but it will not be operable after. You might have to replace the circuit breaker. That's type 1. Huh? It will survive enough to open the circuit breaker, but it wouldn't be operable after that, meaning you have to change it. That's acceptable by the code. Nobody got killed. We did not blow up the switch gear, right? Safety. But you have to go change your circuit breaker, put a new circuit breaker there, with minimum damage to the surrounding. Minimum damage. Okay, that's type 1. You can achieve that one with circuit breakers. Type 2 is you have a short circuit condition. Nobody got killed. your circuit breaker survived, or if your circuit breaker survived, fuse will blow up because you have to put new fuse, and your downstream VFD did not burn, mind it. Your soft start downstream did not burn, as in circuit breaker. It could burn in circuit breaker, and you just flip that circuit breaker or change that fuse, and you're operable. The only way you can reach type 2 protection on a power system is, my understanding is, if you have a low peak current limiting fuses, because it will not only trip, but it will trip fast. That will limit the amount of energy. So that's why we see a lot of electronic equipment will have, after your circuit breaker, they put a couple of fuses in them to protect them upon the existence of a short circuit. You don't burn them. So if you put a couple of them here, you can see how the energy is limited all the way down if you have a short circuit right at this level. So it's all about you on the left. Is your equipment so important, like VFD, soft start, a UPS, that you really need to protect it from, protect the equipment really good, now, so you can reuse it, or it's not? So, any comments, guys? Any questions? So that's your type 1, type 2 protection. Both of them will meet the NEC code book. Electrical system coordination, that's what we just talked about, where an orderly shutdown is required to minimize the hazard. System of coordination based on the following conditions shall be permitted: coordinated short circuit protection or overload indication based on monitoring system or devices. Hospitals is a good example. Emergency system require an overcurrent protection, require by code. Hospitals, because they have essential systems, require emergency system. If you have an emergency panel, require fire pumps, elevators. If they're fit from the same feeder, you have multiple elevators in the same feeder. By code, you're required to have an overcurrent protection device. I'm saying required by code. Now, every engineered project that we do will do it, because that's above and beyond. And now, with 70E, require you to have an arc flash label and an available short circuit on every main, right? You know, the change in 2011. 2011 NEC code book require you every service panel in RMM1 must be labeled with the available short circuit right at that panel. How are you going to get that one? You have to run a short circuit analysis. With that, because of this, and because of the arc flash label, you're almost always, 99% of the time, if you have an engineering project, you are looking at a short circuit study done on coordinated overcurrent coordination as well as an arc flash study. Because of all this. So overload indication based on the monitoring system, you can monitor your system for overload and tripping them. If you have building automation system and you have a SCADA system, you can easily look at these electronic circuit breaker and you see if they're overloaded and shift loads around just for the overload condition. So that's your coordination. Ground fault protection. When the current becomes so high, guys, I want you to give you a break because I don't want you to go to sleep here. Okay, give me a second here. When the overcurrent protection device becomes so high, like 1,000 amp, the ground fault becomes high enough on a 4,000 amp switchgear, on a 4,000 amps, in a 1,000 amp switchgear, like 480. The ground fault current becomes high enough to burn your building, but low enough to sneak under the eyes of the 1,000 amp circuit breaker and not trip. So the smarter than Chad, after we burned a few buildings, we realized that. So we said, if now the requirement by the code says, if your system is 1,000 amp or more, if your system is not 1,000 amp, don't think about it. It's recommended, but not required. 1,000 amp or more. If your voltage is 480-277, this is the worst arcing and sparking and blasting and shocking voltage that you can encounter, right? Worse than 208 and 240. If you have a 480-277, 1,000 amp or more, you're required on feeders and branch circuits and services to provide a ground fault protection. This is a tiny couple of sensors. Let me go to phase A, put the sensor on it, phase B, phase C, and the neutral. And they're looking at the current coming out and the current coming in and back of the neutral. There's substantial difference between what come out of the three-phase, what came to the neutral. What do you think, where this current went? ground, and they can trip or alarm. So that's your ground. So it could be a sensor that operates a disconnect, or a circuit breaker that trips through the operation of a supply circuit overcurrent protection device. Okay, so that's your ground fault protection. Interrupting rating, if you have a circuit breaker, guys, they have 100 amp, 10,000 amp interrupting rating, 100 amp continuous duty rating, or normal operation rating, they call it. So the highest amount of current under rated voltage that the current can safely interrupt. So that's your interrupting rating on circuit breakers. We have, you know what? Let's take 5 minutes. Should we take? That's a good breaking time. Let's take 5 minutes. I know you just guys got 8 and it's getting tough. And I feel sorry for the low voltage guys and gals, because this is really above people's heads sometimes. How many of you guys size conductors? How many of you guys have sized a conductor taking into consideration the short circuit? I guarantee you, unless you did medium voltage, you never thought of short circuit when you size a conductor, right? Now, when it comes, this becomes very, very important, guys, when it comes to high voltage. So let me show you an example. So suppose that you size a conductor, and based on the size, this is right here, short circuit in thousands of amps. So suppose that my short circuit is a 20,000. Can you guys see that? So 20,000. Now, if I trip within one cycle, am I here? Is that the same line? Yep. So yep, it's the same line. So my the size of my conductor is what? Number 4. If I trip within can you guys see within a cycle? Right here, a cycle. You remember what a cycle is? A cycle is 1/20th of a 1/60th of a second. Your size of your conductor to survive this event has to be number 4. Now suppose I have a switch gear and I can turn this circuit breaker, dial it. Can you guys see that dial? When you dial the circuit breaker, delay the tripping of your circuit breaker up to 30 cycles. Up to 30 cycles, then this will continue. Is that 30 cycles? So that's curve 1, 2, 3. That should be right here, right? Oops, right here. Is that? Okay, now that's it right here. So that's my 30 cycles. Now if you guys go down here, so we're close to this, we're somewhere between 2-aught and 3-aught. So what do you think you're going to do? 3-aught. So the size of my conductor have jumped overnight from number 4 to number 3-aught, depending upon how fast I can crank my circuit breaker to trip. That's the concept of sizing for thermal damage. They call it thermal damage. The thermal damage capability. Let me show you one example that I did calculation here based on thermal damage. How many of you guys heard of thermal damage for conductors? So look at this. Here's a fuse. Let me see. Okay, click here. There you go. This one here. Oops, not that far. And this one. What you're looking at is a transformer protected by a relay. Here's the conductor that feeds this transformer. If the conductor that feeds this transformer is sized this way, that circuit breaker right at this value will start burning before the relay picks up and trip. So that's basically the curve that you're looking at here is called damage curve for conductors. Here's my damage curve. This is my damage curve for conductors. It's a number 6. So if I set my relay the way I'm setting it right now, And even if I put an instantaneous in it, let's go put an instantaneous low. I put my instantaneous. Can you guys see my instantaneous jumped in it? I want you to pay attention to this. Here's what my relay is going to pick. If the short circuit is right here, the conductor is protected. If the short circuit is right here, the short circuit will go up, time. It's going to hit the curve. The curve starts burning. Then it keeps going up. It hits the circuit, the curve of the relay. Now the relay is going to wake up. Great. Now your relay woke up after your conductor burned. Is that what you wanted to do? So in a case like this, in order to adjust, so you have to go to your curve and increase the size of your cable. My cable is number 6. Look, I'm going to go to number 1/0. Number 1/0 almost can't make it here. So, or I can adjust my instant. Can you guys see how I can adjust my instantaneous? I can put my instantaneous right here. Now I have full protection for my curve. Big deal when it comes to protecting your curves.
So the wire gets hot so instantly it acts like a heating element.
Well, it starts melting the insulation. Yep, and start after melt the insulation, catch up fire. Of course, you're in a conduit, but after and then when your circuit breaker it will trip. You have to replace all your cables. Is that why you have a circuit breaker though?
So when you're designing this, you have to specify how you're going to set your circuit breakers before you know what size wire you're going to pull.
That's what your short circuit analysis is. So when you set your relays, you pick, I put number 6 here. When I set my relay, I put my conductor. I can tell by putting my relay here, my relay cannot protect this conductor. So I have two options. Either I will lower the setting of my relay or increase the size of my conductor. If I lower my setting of my relay, well, Chad, how about if you put it too low here? So see what happened? If you put it too low, this is the rush of the transformer. That's protecting the transformer primary. If you put it right here, every time you energize the transformer, bang, it opens. Is that what you want? So you have to clear that little point. So they have restraints on you. So you have to, your restraint is right here. You have to clear that voltage. Okay? Then you need to see what conductor can get you there. So now here's my conductor. That's my restraint on this. Here's my conductor. I can go, let me see, go lower to, that number 2 is not lower, Chad. Let's go to number 4. See, number 4, barely cutting it here. So I have to go next standard, number 2. Number 2 will get me there, based on the setting of my relay. So you start sizing your conductors based on the short circuit settings of your relays and circuit breakers. That becomes a big deal. Mind it, I'm using an IEEE. This cable. I don't know how many of you have paid attention. This is a 50,000 volt cable. That's a big deal when it comes to higher than 600 volt cables. When it's 600 volt cables or less. Speaking of which, you guys know in 2014 they changed the limit of the voltage now? Anybody heard that? You no longer say over 600 volt or 600 volt or less, over 1,000 volt or less. So they're using the 1,000 volt as a limit. 600 volt. No, they say, but when you go over 1,000 volt, then you have a special requirement for equipment. Under 1,000 volt or under, a different requirement for equipment. That's it. Coffee breakdown. Yeah, they're not going to change the THHN into 1,000 volt, but there will be a lot of conductors that will have 1,000 volt insulation. Okay, so that's your damage. So please, if you haven't heard the word damage curve for cables. So remember the damage curve with your friend Chad. So that's my overcurrent protection device. So I know every time I teach this one, I've been doing it for many times. Nobody from the low voltage guys have ever heard this. I mean, this is a lot of most of the engineering, even though in the code, it's old code. damage curve, and so forth. Here's number 14. Look at that. These are direct figures. Number 14 can handle 4,800 amps for a quarter, 1/8 of a cycle. Well, that's too low. Here's a quarter of a cycle. That's when the fuse is going to trip. This number 14 conductor can handle 3,400 amps. If you tell somebody like this, they'll say nuts. But for how long though? 1/8, 1/4. That's when your fuse is going to operate. Here's when your circuit breaker is going to operate typically 3 cycles. How much current that conductor can handle for 3 cycles? 1,000. If you don't open in 3 cycles, or if you're pulling more than 1,000 amp, your conductor will burn. So in the low voltage world, and that's number 14, of course, you have all these numbers. These are called the damage curve for conductors, depending upon the installation that they have and the installation rating. This one, guys, shows comparing the 5 cycles for different type of conductors. How can it, equivalent grounded conductor short circuit withstand? So you have a number 14 can withstand this amount of current for 5 seconds. Remember, is a 5 seconds. If it's rated 150 degree, 250, and all this temperature that they can. So we'll give you guys the amplicity, basically related to the damage curve for the conductor based on multiple standards. So you take 14, 97, 137, and 258. This is 1 amp, 30 centimeter validity. There's different sources that they use. So long story short, these are how we calculate the short circuit withstand rating or damage curve for conductors. Damage curve for conductors. The tables, these are the point. These are coming from a lot of this information from this book. And it's a little bit biased too because they're fuse guys. So, but most of this information is fuse book. I did not verify. I get my information from the SKM, so I really don't use these when I size directly from SKM. SKM company in California, well known, they've been in business of short circuit analysis and all this stuff for years, so we trust their info. Long story short, guys, based on the setting of the circuit breaker and the short circuit availability, a number 10 conductor, ground equivalent ground conductor, can protect you or not protect you. So here's number 10 equivalent ground conductor. A fuse, 60 milliamps. Look at the opening. It's going to open in a quarter of a cycle. This circuit breaker is going to open in a cycle. So because this is fast, the equivalent ground conductor will survive. Because this is slow, 1 cycle is slow compared to a quarter of a cycle. That's 4 times faster. This circuit breaker might be sized bigger. Look at that, it says 2 watt. I've never had a situation when in 600 volt or less, if you size your equivalent grounding conductor based on 250.122 and you're grounding electrode conductor and bonding jumper like we did based on 250.66, we don't have any issues with and you set your circuit breaker probably appropriately, as in fuses and circuit breaker will open within 3 cycles. Your ground fault will be, that conductor will be large enough to carry the ground fault. What they're saying here, because you allowed the short circuit to sit on this number 10 for a cycle, you have to up the number 10 to 2 watt, option 1, or you have to increase the speed of this circuit breaker to a quarter of a cycle. How would you increase the speed of a circuit breaker to a quarter of a cycle? You can't. You basically redesign the circuit breaker, right? Or replacing it with a fuse. So this is just emphasizing the idea of a short circuit. Current limiting fuses, you guys familiar with current limiting fuses? When you have a current limit, we will have it here, okay. Current limiting fuses, when you have a current limiting fuses, when it operates within its operating limit, it will knock down the current, the instantaneous, as well as the RMS value. And I do have a couple of examples later on how current limiting fuses will work. Current limiting fuses, they're awesome in terms of knocking down the arc flash energy and the blast that's coming out of the system. We'll talk about them later on. Overcurrent protection device, guys, any current in excess of what the equipment are rated for or what the conductor are rated for because of overload, short circuit, or ground. We talked about this one before. Overload, so overcurrent is overload, short circuit, and ground, right? That's how they define overcurrent. So when Kiljic yesterday, you guys do motors, right? You read motors. When he talked about the overload, that overload that we add to the motors, this is above and beyond the already existing overload component in the circuit breaker. Because motors are very expensive, very sensitive, so we need extra overload protection. Though the circuit breaker will provide you an overload, but we need more above and beyond what the circuit breaker or the fuse provide you, so we have a separate overload to protect these equipment. Overloading an equipment, guys, is operating in excess of its full load. So you have a motor that's supposed to run at 100 amp and you're pulling 150. How would you overload a motor? You know, a motor is supposed to pump water to the second floor, rated for 2-story building. You install it on a 15-story building. That's kind of too much. Or an elevator that's supposed to handle, I don't know, 10 people for a total of 100 pounds, and you load it with 20. So, so momentarily, you could overload condition. Okay, short circuit element overload. Some of dual, when it comes to fuses, guys, you're familiar with the there are different type of fuses. The notorious, the famous one is dual element time delay fuse. Dual element time delay fuse is almost a circuit breaker. Can look at the overload component and the short circuit component. So they have two components on them. One will melt upon the existence of short circuit. One will melt upon the existence of a ground fault, of an overload. So because you know what the overload is? The overload typically tends to be smaller amps for a longer time. Short circuit typically tend to be very high amps for very short time. So they design these links to burn at different, one is too much amps, little time, the other one is too little amps, well, more than that, more when it's rated for, but for a longer time. And all these are coming from the circuit breaker. Supplementary overcurrent protection device, these are up to you guys. So you go to your VFD, the manufacturer might stick a couple of fuses inside the VFD to protect their equipment. These are above and beyond the brand circuit overcurrent protection device, the feeder and the service overcurrent protection device. So this limited protection is in addition to the protection provided with the required brand circuit. So certain equipment manufacturers say we are not going to depend on. A good example of this is chillers, any chillers or condensing units or so forth. What they do is we provide, say, a 40 amp 480 feeder to the chiller. Right next to the chiller, they have a fuse disconnect that they rated certain fuse to protect their equipment, and we just tie to the line side of disconnect of that chiller. These are supplementary overcurrent protection device. In addition, luminaires, appliances, components shall not be used as a substitute. So this is just emphasizing you can't use it. It has to be above and beyond the short circuit, not in replacement of the overcurrent protection device. You guys don't. How many of you deal with higher than 600 volt? There's a few definitions that we use with higher than 600 volt. We barely using Chad 120 volts. Now you're going to higher than 600 volt. I want to remind you the code have replaced this one into a higher than 1000 volt now, 2011. So a couple of definitions: electronically actuated fuses, and I'm going to move forward. These are intelligent type of fuses, guys. They have a time current characteristics. They can sense that you have a short circuit. They're used as 5K, 15K, or 25K volt. They sense they have a overload condition, and they initiate a triggering mechanism. So they will trip like a circuit breaker. So current characteristic energy to initiate triggering and an interrupting module that interrupt the current when an overcurrent condition occurs. They can also be current limit fuses. These. So these are smart fuses. Fuse, typical in a high voltage fuse, guys, is a dumb fuse overcurrent protection device with a current with a circuit opening fusible part that is heated and secured by the passage of the overcurrent protection. That's a dumb fuse. There's no intelligence in it. It's like any other fuse that you have in a low voltage. It sends piece of little wire size appropriately. Too much current goes through it, burns it. And then they have a couple of insulation or a couple of fire extinguishers inside it. Material. Controlled vented power fuses. When it opens in high voltage, the interruption is such that no solid material may be exhausted into the surrounding atmosphere. When you have a high voltage current, if fuse open, you can have a lot of energy that will be vented to the outside. If that fuse is inside a building, do you want this energy to blow up in the building and burn something? No. So they'll be non-built. If this fuse is the top of 40-foot tower, 40-foot pole, do you care what's going on right at the top of 50? So you see the bam and big explosion come out and interrupt the circuit. So these are the controlled vented versus explosion fuses, sir. Questions? No? It's like an option. If you move your hand, you buy, man. Be careful here. Explosion fuse unit. Vented fuse unit in which the explosion effect of gas is produced by the arc and the lining of the fuse holder, either alone or aided by the spring, extinguishes the arc. So they use the effect of the explosion to actually extinguish the arc. When it comes to overcurrent protection devices, guys, the single most design-wise, and I'm not a manufacturer, the single most important thing is how are you going to interrupt this huge energy without burning the surrounding? So they have three technologies that they do. They have air circuit breakers, contacts open in air. That's the cheapest that we use in the 600 volt or less. Then they have, the break can be electronic or thermomagnetic, but the mechanism of interruption, 3000 amp going through this contactor. Can you guys imagine what an 85,000 amp short circuit is? That's like you driving your car, God forbid, at 95 miles an hour down 35W, and in front of you is a semi, right? You're also going at 95 miles an hour, and all of a sudden the semi put the brake on, and you hit the semi in the back. That's what an 85,000 short circuit incident is in a power system. What's going to happen? You imagine the impact. That's what the circuit breakers need to be able to handle, interrupt that energy at an 85,000 amp. So it's a huge energy, big mess. It's going to happen. So you need to interrupt this, to interrupt the arc. They use either air for low voltage. Then for high voltage, they use oil. Now you talk about oil circuit breakers. Utilities use them all the time. And then the next step is vacuum. So they interrupt in the vacuum tubes. There is no air. They have vacuum tubes and they have the contacts inside them, empty from air. When they interrupt in vacuum, there's no arcing. If they interrupt in oil, the oil will extinguish the arc. When they interrupt in air, they have air chokes or whatever they call them, so they direct the arc away from the contacts. As the arc comes and you interrupt it, it takes it away from the contacts, so it saves the contacts. Arc shoots, thank you. Arc shoots. So all these are ways of interrupting that huge amount of energy. Non-vented power fuse without intentional provision for the venting, escaping of all the stuff to the atmosphere. Vented power, it allows this stuff to go into the atmosphere. Power fuse unit, this is the fuse and all what goes into it, and the unit that you mounted at. Multiple fuse assembly of 2 or more fuses. We can parallel fuses, believe it or not, like this, parallel fuses. Okay, so that's basically it in terms of the high voltage. Any comments, guys? I don't know about high voltage fuses, but really the major things in high voltage fuses is what do you do to extinguish the arc when you open these contacts? What's your method of extinguishing the arc?
Yes, you have those fuses in parallel. Do they all blow at once?
If you have a short circuit condition, right in here, and you're paralleling them, would they all flow at once? They will all see it, and I believe so. Yeah, they will all see the short circuit, and the reason why they parallel them, it gives you more amps. So you can have 100 amp and 100 amp and 1,000, 1,000, 1,000, 1,000, 4,000 amp system. That will give you all this will pull 1,000. Each one of you will see 1,000 amp. If you have a short circuit, right in here, they will all see the short circuit. They will trip.
1,000 amp fuse.
Yeah, 1,000 amp fuse. So they on the overload. I've never designed the lines. They use them in the high voltage. On the overload, on a normal operating condition, it gives you the ability to break in sections. But in short circuit condition, I believe, unless they rate them differently, I believe they will trip. They might, I don't know, they might, it depends on the curve that they're using in them. Some of them might be more faster than others. Some of them, yeah, I would say that
one trips than the other ones would, if they're at
Would immediately fall.
Yeah.
Each one would be like 1,300, 1,300, 1,300.
good point. That's if the system is fully loaded.
Right.
How often your system is fully loaded?
You
You guys,
trip.
yeah. How often is your system is full loaded? If you have a short circuit condition here, and if this is open, and these continue to operate, what's going to happen to the short circuit? You're still pumping current into it, so they almost all have to open. Almost all have to open to clear the fault here. So, assembly fuses, okay, flexible conductors. When it comes to protecting, so overcurrent protection device guys protect conductors based on 310.15. You guys are familiar with 310.15. For example, a number 14 conductor cannot be protected with an overcurrent protection device more than 15 amps. What's the exception though? Motors. If you have motors, you have an exception for motors. So I could have a 50 amp fuse tied to a number 14 conductor that feeds a design B motor. And that's completely legit. Why? Because the motors, like you saw yesterday with Kelvin, have an overload protection that protects the motor. And as you protect the motor and limit the current that goes through the motor, you're also limiting the current that's going through the conductor, right? Because whatever current goes through the motor is going to go first where? Through the conductor. So if you're limiting the current that goes through the motor to say 10 amps, and your circuit breaker is number 14, then you are in a sense limiting the current through the conductor to number 13. Number 13. Okay, so protection of conductor devices rated 800 amps or less. What they do, guys, if you have a feeder, I can't envision using like an 800 amp that feed multi-outlet assembly, multi-outlet branch circuit supplying cord of one connected and so forth. A single conductor does not correspond to the second. So if you have take this. If you have a 400 amp, if you have a 400 amp feeder, and I use this one all the time, you have a 400 amp feeder. Let's go to this. Here's my 400 amp feeder, and that's feeding a panel, lugs, main lugs only, and my 400 amp feeder. What size conductor do I need for this? Well, I'm going to go size of 500 kcm, 500 kcm. You guys are familiar with 500 kcm. The 500 kcm, guys, can get you 380 amps. Okay? So now I have an overcurrent protection device that's 400 amp protecting a conductor that's rated for 380. Is this okay? Completely legit based on this rule. Why? Because the next standard overcurrent protection device from the 380 is what? 400. Now, if you're using an adjustable circuit breaker, then you have to use the adjustment of that circuit breaker as your next standard overcurrent protection device. Now, make this is an 800 amp. This is an 800 amp, typical. Then this will be 2 sets, right? 2 sets in every phase. And this will be multiplied by 2 now because I have 2 sets. And that will get you 760 amps. Is this legit? Yup. Why? Because the next standard overcurrent protection device is what? 800. So that will allow you guys to have conductors protected by an overcurrent protection device that the conductor is slightly less than what the overcurrent protection device is rated for. Now you hit that ceiling that's called 800 amp, then you start matching your conductor to the overcurrent protection device. Example, 1000 amp circuit breaker. When you land on it, you have to land 1,000 amp worth of cable or more. That's it. So a lot of contractors love to take advantage of these rules. The only exception, of course, it has to be the next standard, and you can't use plug and connected equipments, portable, cord and plug connected portable modes. So you're dealing with panels and so forth. So that's your conductor. The small conductor rules, guys. The small conductor rules in NEC code book says 14, 15, 12 aluminum, 12, 15, 12, 20, and 10, 25 for aluminum, and 10, 30. So between the 30, the 20, and the 15, 14, and 12, and 10, that will cover, I guarantee you, that will cover 90% of your lighting and receptacle brand surface. It's not all of them. I mean, typically your lighting circuit is 20 amp in a commercial building. Your receptacle circuit is 20 amp. 20 amp is number 12, and you might go for a lighting circuit of 30 amp and pull number 10 into the boxes and tap with number 12 to the other lights. We do that sometimes. So that's about it. Have you guys ever pulled a lighting circuit more than 30 amps? Even 30 amps, very few people pull. So between these, that will cover, I would say, 90% of your lighting circuits and small equipment circuits, as well as your receptacle circuits, which is the most convenient brand circuits. So because they're most convenient, because the public is exposed to them a lot in dwellings and non-dwelling, the code limits the amount of current that can come out of it. Even though, guys, number 12 copper can get you 30 amps. Based on the code, it can give you 30 amps on the 90-degree column. But we don't want to pull out of it more than 20 amps. So these are small conductor. These are, I want to remind you, this says fuses and times shall be considered. These are fixed circuit breakers and fuses. A standard size is fixed and circuit breakers and fuses from 15 all the way to 6,000 amp. The most utilizable ones are 15 to 3,000. 4,000, I have a few projects. I've never done anything higher than 4,000. Anybody have done anything higher than 4,000? 5,000, 6,000? But what I heard about these, they use them 5,000, 6,000 when you have 8 generators, 1250 kW each, all coming to a one assembly switch gear. So they're pumping 6,000 amp into that switch gear. And what they do, did you guys see something like that? 6,000 ampere, yeah. On generators, yeah. So what they do is they bring here's my 6,000 amp here, and then in between the switch gear, the switch gear is 6,000 amp, and then here they can pull loads between every circuit breaker. So every generator will be coming in, and between every 2 generators they pull a load. That's what we've seen. Between every generator they pull a load. So the idea is this is 6,000 amp switch gear, 6,000 amp circuit breaker, and we're pulling all the loads from it on the switch gear. That's the only. So, do you guys have generators, all of them? Yeah. Okay. Big generators, but Excel will never give you more than 3,000. 4,000 you have to peg a little bit, but I don't know about other utilities. Did you guys install a 4,000 amp services? 4,000, but they wouldn't give you more than 4,000. They like to even limit you to 3,000. If you want more than 3, they give you 2 3s or 3 3s. Reminder, these are fixed, non-adjustable circuit breakers. You can have adjustable circuit breakers. For adjustable circuit breaker, the ones that I showed you, the limit is the sky, right? I can almost get, you can imagine, if you have adjustable circuit breaker, you can have an 800 amp circuit breaker and adjust it in increments of 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, and that's the adjustment that you can do. You can imagine every one of these, if it's an adjustable circuit breaker, imagine 10 settings, extra settings. So take that 100 amp and you can adjust it in increments of 0.1, 0.2, 0.3, 0.4, all the way to 1. Almost. And some of them have actually 0.95 even, and 0.85. But generally speaking, any one of these, starting, I mean, it doesn't make sense. Starting from the 100, I would say up. Any one of these can be adjusted if it's an adjustable circuit breakers in an increment of 0.1 up to 1. If that makes sense. So yeah, the limit, it becomes so many seconds that you can have. Am I the only one who's excited again here? That there's so many circuit breakers. So 15 and 20 circuit breakers, you guys would do dwellings, right? 15 and 20. 15 and 20, these are equivalent to, I grew up in Jerusalem wiring. This will be 10 amps, and this will be 16 amps, typical. And that will be, you will pull 1.5 squared millimeters and 2.5. Exactly the same, number 14, number 12. And between these two, you have covered 90% of your house. Between these two circuits. So it's really interesting how the amps are different, but the concept is the same.
Can you still overload that 60 amp breaker to 80%?
It's limited to 80%, yeah, continuous load limited to 80% of that rating, continuous load. But in-house, there's no continuous load. The lights, well, I guess if you're using it here in the building, that will be receptacles are non-continuous load in a commercial or anywhere else. Lights are the only continuous load because these circuits are lighting and typically they're lighting and receptacle loads. So yeah, you have to limit it. Space is about electrical equipment. The NEC code book, guys, as well as 70E, requires you to maintain clearances because of the shock hazard and the arc flash hazard. So you have arc flash boundary that you have to maintain based on 70E. The NEC code book 110.26 give you the minimum clearances around electrical equipment, and I was talking to a couple of guys when we were eating and saying that we need more space around the equipment, and I said as engineers we always go to the architects double the value. So if you look at all the scenarios that we have, we need for typically the largest space needed in front of the electrical equipment is 4 feet deep. The width of the equipment to the height of 6 feet or the height of the equipment, 6.5 for the height of the equipment. That's your working space. So when you go to the architects, we tell them we need 8. Then we compromise to 6. So now we have 2 feet extra more than what we need. So that's for your safety. So here's what you're looking at. The width of the equipment, the height 6.5 for the tall people so they don't hit themselves in something. And the depth, depending, the depth can go minimum 3 feet to a maximum of 4 feet. The only time you have 4 feet if you have energized panels facing each other. And one of them is 48277, you get into 4 feet. And there's rules for large electrical equipment, 1200 amps or more, and more than 6 feet, then you start doubling the distances between them or have 2 entrances and so forth. So this is strictly, guys, to get you access to your electrical equipment, strictly giving you access to electrical equipment to work on it energized, to work on the electrical equipment energized. Supervised industrial installation. Now, most of you guys would probably don't work, I don't know, maybe you work with industrial supervised installation, where you have, here's how they define it, 2.5 megavolt amp, the size or greater. If your facility is consuming 2.5 megavolt amp or more, and the voltage to ground is higher than 150, so you're looking at 480 or 600 volt. That's qualify for industrial and manufacturing processing. That and qualified people like yourself maintaining the system, then the code relax the rules. If you're under these circumstances, but look at the qualified people maintaining the system, 2.5 megavolt amp size of service coming to it. The voltage is 48277. Then you're looking at relaxing a little bit of rules. They relax the rules in overcurrent protection device and so forth. So is that your facility, guys? Something similar? Okay. So they have a few relaxation for the equipment. We talked about the ground fault protection for equipment, guys. We said the rules for the ground fault protection shall be provided solidly grounded. It has to be, do you guys remember the word solidly grounded? We just talked about solidly grounded. If you have impedance grounded, do you need it? No. You have a ground detectors on that, not ground fault protection. So there's ground detection. So 150 to ground, so that will limit you to 482.77, 1000 amp or higher. Then you have to have an overcurrent protection device. The only exception for this is fire pump. Do you really care if you have a ground fault and your building was on fire? I don't think so. So let the fire pump run. No ground fault on it. Installation with ground fault protection is provided at the surface of the feeder, so you have a supplement. You have something to protect you. Or you are cooking in nuke or chemicals, and you really don't want to trip on a ground fault, right? So industrial process where non-orderly shutdown introduces additional hazard. You're cooking chemicals in a chemical factory or petroleum, and if you interrupt that process, you create an explosion. You know, so these they don't want you to put ground fault protection because you could trip, interrupt the process, and that will create more hazard. So you can see so like here you're choosing between the necessary evil. The evil number one, you have a ground fault that could burn your building, and necessary evil number two, you have an explosion because of the chemical plant that you're working that could burn the whole plant, or a fire pump that's not going to work when you have a fire. So these are exceptions to the ground fault. Other than that, you have to have a ground fault protection. And the ground fault protection, guys, looks at phase A, phase B, phase C, neutral, sees what's coming out, must come either equal itself there, or comes the rest, what's not equal is going to come back. If there's substantial difference, if it's a ground fault protection, will trip. If it's a ground fault alarm, it will alarm. And it has the capability of tripping or alarming. Tripping or alarming. Okay, ungrounded conductors must have an overcurrent protection device tied to them at the point where they get in series, where they get their power. And the overcurrent protection device must open circuit breaker as an overcurrent protection device shall open all ungrounded conductors manually and automatically. Fuses don't have to. Fuses don't have to open all the phase A, phase B, phase C simultaneously. Circuit breakers do. Multi-wire branch circuit and location of ungrounded conductor. Single pole circuit breakers with or without identified handles. When you have grounded single phase, so look, this is where you put in a multi-wire branch circuit in 2008, guys. Do you remember the major change that happened? They said if you're pulling a multi-wire branch circuit, you must tie the single pole circuit breaker with an approved handle. You guys remember that major change? So literally, you have phase A, phase B, phase C with a common neutral coming here. They are coming from 3 single pole circuit breakers. You have to tie them together. What's wrong with this? What's wrong with this? If you have a ground fault in this circuit, could, depending on how big and the size, it could literally physically pull, because they're tied together, it could pull the other two with it. Who cares? Now that's compromising the integrity of your power system, your lighting system, right? You know, you have a ground fault, you want to trip one circuit, not 5, or not 3 with it. So that's the tying in. So grounded single phase and 3 phase. So where would you use single pole circuit breakers tied together with an approved handle? Well, you use them in 24120, easy, right? Single line to neutral load. So if you have 24120, 28120, line to neutral load, like lighting load, receptacle loads. For 8277, line to neutral load, no problem. Like you have 277 lighting circuit, 277, 277, phase C, B, A, common neutral, no problem. As long as the load is line to neutral. You can put them in any grounded circuit as long as the load is line to neutral and you tie them together with an approved handle and you pull a common neutral. Now for 208 and 240, you're allowed to also put them if the load is line to line. For example, your air conditioning at your house. The circuit breaker that feeds it can be 30 amp, 2-pole circuit breaker, or can be 30 amp, 2 single pole circuit breakers tied together with an approved handle. So either one of them will. We can't do this one on, we can do in 208, not a good idea, but we can do it in 208, 240, line to line, but we cannot do it in 480. So air handling unit. You have a 40 amp air handling unit. Can I use single pole 1, 2, 3 tied together with an approved handle and feed them 480 to the air handling unit? Not approved. Does it work? Yes, but not a group. Because if one of them open, guys, you're dealing with open phase on an air handling unit. So that's what this is telling you. Where would you use a two single pole with an approved handle to tie them together? Now, recommendation, being an engineer, the only way you should think of this is really if you're tying line to neutral load, like lighting loads, receptacle loads, equipment loads that line to neutral. Every time you tie line to line equipment, like 208 or 480 or 240, you should use two pole circuit breakers. It's more reliable, trips better, and so forth. But though you are allowed to put a 240 circuit, two single pole circuit breakers on a 240 lighting load, a 240 load, as well as a 208. Any comments, guys? Any questions? So you're looking at here, permitted for single phase line to line load. Single phase line to line load. So I can take a 208 phase A, B, and go feed a range. Or a 240 phase A, B, or hot 1, hot 2, and go feed a range. Single phase line to line. Like everybody knows that you either feed single phase either line to neutral, line to line, and three phases have to be three lines. Any comments, guys, about tying these circuit breakers with an approved handle to feed loads that are neutral loads or line-to-line loads? Line-to-line loads. So, or you can also use them with a DC system, 3-wire DC circuits in a grounded system, individual single-pole circuit breaker with an approved handle permitted to protect the ungrounded conductor for line-to-line or line-to-neutral in a three-phase circuits in a DC 3-wire circuit. So shall be provided with a means that will simultaneously disconnect. It came in 2011, guys. Here's a multi-wire branch circuit. You have to simultaneously tie these circuit breakers together so they can trip together. Also, I don't think it's 2008 before. If you have a multi-wire branch circuit coming in, you have to identify the neutral that goes with each multi-wire branch circuit, unless they are obviously or clearly obvious. For example, you have two cables coming in here. Every neutral in every cable is a multi-wire branch circuit. I have a conduit like this, and I have two conductors, 2, 4, and 6. 6 conductors coming in. I can tell which neutral goes with which circuit. In a case like this, you have to identify them, group them together. Do you guys remember that? I think it was in 2005 came, not 2008 though. Anybody remember when it came to be?
I think you have to put a marking on the neutral too.
Mark it as in, well, that's if you have,
Identify the end of it as a multi-wire neutral.
well, that's, you have to identify it as, all conductors of multi-branch circuit shall originate from the same panel board or similar distribution equipment, and have to be identified at the point where the branch circuit originates, and you have to identify with the panel. So the only thing you have to clarify them if you have different voltages. We're talking about like you have a 480, 277, 208, 120 panels, and you have to use the entering the same box, gutter, or what so forth. Then you have to use a different color-coded neutral. Is that what you're saying?
That's what I've heard.
Yeah, if your building has two voltages like 480, 277, 208, 120, then you have to identify the phases, every system by phase and by system. So you have to color code the systems basically for feeders and branch circuits. Branch circuits only if they originate, if they are in the same gutter or the same box or the same conduit. So if they're not in the same box, gutter, or conduit, so like this panel is 480, all the conduits 480 are separate from 208, then you don't have to identify the branch circuits. What they don't want you guys to do is open a box there and two whites. Which one of them goes with 208 and which one of them goes with 277? Would you be confused? Anyone can be confused. Now you open a box and you see one gray and one white. It's very clear. And you go to the panels, and every panel is say gray is a neutral of 48377. White is a neutral of 28120. Okay, then you know that. And in the same box, you have red, you have black, red, blue, identified as 288, and orange, yellow, what's the other one? Brown, orange, yellow. That will be the 480. So they just want you to identify the phases if you have two different voltages in your system. Shall be grouped in at least one location within the panel or other enclosures. That's where you group them, identify them. Grounded conductor, we talked about the grounded conductor. You no need to put the overcurrent protection device, opens all. You cannot interrupt the grounded conductor. Can I put a fuse in the grounded conductor? I can't put a fuse in the grounded conductor. Except if it's DC. They take the negative, like I told you, and they bring it to a fuse. Out of the fuse, they go to the ground, because if they have a ground fault on the roof, they want to be able to trip that fuse and not burn the roof because of this current, the short circuit there. So that's the only place that we put them. So that's, you can't put the overcurrent protection device, opens all, unless you have a 4-pole circuit breaker, so you can interrupt the phases and the neutral at the same time. That's an exception. Or if you're using it as an overload. If you're using it as an overload. I don't know if I have a picture for that one. If you're using it as an overload. Any comments, any questions, guys? Comments, questions? So in a delta grounded system, here's a delta, and corner grounded delta. If I ground that delta, I don't know if Jeff showed you that one yesterday. I can have a fuse disconnect here, and another fuse disconnect here, and a third fuse disconnect here. Now, even though, remember, this is grounded here, the only exception for this, if I'm feeding this to a motor, and this fuse have dual function. Function number one is overcurrent protection device, which is, I mean here, short circuit and overload at the same time. So if you decided to use the fuse as overload and short circuit protection at the same time, which is allowed by code, not a good idea on a bigger system. Anybody knows why not a good idea? Now you don't have a backup for your overload. If that fuse is to malfunction, you burn your equipment. If your overload malfunction, you still have a backup overload protection through the fuse or circuit breaker. That's the only place you can put a fuse in.
Is that grounded conductor considered a neutral or a phase?
No, it's not a neutral, it's a grounded conductor.
Grounded phase conductor.
A grounded conductor. That's corner grounded delta. Anybody dealt with corner grounded delta? Corner grounded delta. That's when you have a delta and it's causing a lot of transient in your system. You will stabilize that delta. The cheapest way to stabilize it is ground one corner. But what's wrong with this? Now you got a grounded system, so you lost that advantage of ungrounded system, which is a ground fault will not trip you. And against this, a ground fault will trip you. A ground fault here, would a ground fault here trip you? No. It has to be on phase A or C to trip you.
You're running that system into a circuit breaker panel. Are you going to 3-phase bars in that circuit breaker panel? Or
The way they run them, there are two ways of their circuit. There's a picture in the book. The way they run these, it's really weird, ugly. You shouldn't use it. What they take is they take this system and they run it into. I'm going to run it from this side. They run these. Let's come from here, and here, and here. So what they do is they run these into a circuit breaker, the two hots, and this one will run into a ground bar. That's how they do them in the panel. That's inside your panel. So really weird, and it caused a lot of trouble. So this will be white conductor, imagine here, and coming to a ground bar here, and then you have to ground this one in your service, bond it. And your circuit this is a single pole, a single phase panel, fed from a 3-phase system to feed a three-phase load. So if I have say a three-phase machine here, I can, here's my the two phases, and I grab the third phase and take it directly to the machine. So the third phase becomes the grounded conductor bar here. Anybody have seen him? You guys see him? Don't you ever design a system like this. You send an apprentice there, they look at this wide conductor bar, so they grab this thinking they have a neutral. This is very similar to single phase, right? They grab this thinking in neutral, take another phase from here, not knowing that they're pulling 240 to all these receptacles instead of 120. So anything you plug, what's going to happen? You will put 240 across 120 devices. Right. Astoria in Milwaukee, an inspector told me that a guy burned multiple lights multiple times before he realized that the neutral is this voltage is now 120, it's 240. He thought there's something wrong with the lights.
Do you use 2-pole stars or 3-pole stars?
You can use 3-pole if you want to, but the way they use them, they use 2-pole, cheaper equipment. 2-pole circuit breakers. Okay, any comments, guys? Any questions before I flip into my second PowerPoint presentation? Shall we take 5 minutes? Let's take 5 minutes. That's a good breaking time. It's getting tough here to keep you guys awake here. Oh, talk about... Okay.
Motor generator set, and then probably maybe a deep well for like a slot cooler, and then like 8 hours blower. So those are the only two things you have to consider. Everything else you have separate.
So, and they're coming from a corner grounded delta.
Yeah.
Wow.
But then over the years, when people started adding stuff, they started tapping stuff off that.
Yeah, not knowing.
Yeah, or if you're stuck with it, so somebody ties something to the.
Okay. A couple of things, guys, I would like to go over. The tabs of the tab rules. Tab rules when it comes to the overcurrent protection device is a big deal. So we're going to talk about, in the second presentation, we'll talk about the tab rules, the overcurrent protection device location and installation, overcurrent protection device classification, and fault current calculation. I apologize, we were supposed to give you guys a fault current calculators by hand, like paper. If you need them, email me. I'll email it to you. But you actually can get better than that. If you go to Cooper Busman and sign, and they don't give you a lot of junk, believe me. You sign, write your name and company. They send you, this one is a PDF format. And all the short circuit calculation that I'll go over, it's right into this book. So just go to Busman, Cooper Busman, website, sign, and it's called the SPD. SPD 2008 is the latest. I don't know if they came up with 2011 yet. Yes, sir.
Anybody in here got a Sprinter? Sprinter van? No? Okay. Bounce keyboard then.
No, not.
I'll be back.
Okay, thank you. Okay. The location. The overcurrent protection device shall be located at the point where the overcurrent protection device receive the power. Meaning, when you bring the branch circuit here, you put your circuit breaker here and you pull the wire. You can't just pull the wire 2 miles away. You put your circuit breakers. Doesn't work this way. That's called tap. So at the point where they receive the power. There's a couple of tab rules, guys, dear to my heart, and I'm sure it's dear to yours. Rule tab, I'm not sure, but rule tab number 1 is really cool. And remember, Chad thinks cool, everything is cool. So here's the rule tab number 1, and I'm going to summarize it with this way. So suppose I have a 300 amp feeder, you took, okay? And for 300 amp feeder, I'm just going to size that. What's a 300 amp? What would that give me? 300 kcm, I think. Anybody can size that one for me? 310. But So for 300 amp, 280, yep, I can go to 300 kcm because 280, the next standard is 300. Taking into consideration that one 285 amps, the next standard is, so I can go for 300. So this is also 300 kcm. So the conductor size that here is 300 kcm. Cool. kcm. And then I brought that baby in a gutter and I tap it. Now remember, this is inside a gutter. And I'm going to tap it 2 taps. Tab number 1 is 10 feet and tab number 2 is 25 feet. So I'm just going to say 25 feet here and this is 10 feet. Okay? 10 feet. Okay, so these are the most notoriously famous 2 tabs that we guys use. You have a 300 amp. You pull a 300 kcm conductor, put it in a gutter. I call the tabs the poor man's job. Because I don't pay, I'm an engineer, I don't pay for the equipment, I design them, so the rest of you guys have to bend them and pay them. Because what happens if you have a short circuit right here? You lost the whole system. The reliability of a system, that tabbed system, is not the best, but it's cheaper and easy to install and fully understand. You pull 10 feet from here to here, you put your circuit breaker, and then you put your load, let's say panel or load here, and then panel or load here, okay? The 10 feet, this is 10 feet, believe it or not. The 10 feet, let me go see if I can get a different color. So you are the good Samaritan today, huh? It's good. The conductor, how does it look like? Okay, the conductor for 10 feet that you can tap, guys, is, the code says, is 1/10 of the overcurrent protection device. In my case, what's 1/10 of 300? That's the smallest conductor that you can pull. It's 30 amps, right? 30 amps. So for 30 amps, so then you have to put a 30 amp circuit breaker here, right? And what do you guys think the conductor here has to be? What's 30 amp conductor? Number 10. That will be number 10. Can you guys see that? So for 10 feet, the smallest wire that I can pull out of a tab for 10 feet has to be 1/10 of the overcurrent protection device here, which leaves me with 1/10 of 300, give me a 10 amps is a number 10 conductor. So I can take number 10 conductor, tie it to 300 kcm, minimum, pull it all the way 10 feet, land it on a 30 amp circuit breaker, because the 30 amp circuit breaker has to limit the current to the number 10. Can't go more than 30 amps. And then feed a panel, 30 amp panel, or 30 amp heater, or 30 amp motor, or whatever, out of this. That's rule tab, the 10-foot rule tab. The only condition is, number 1, this conductor cannot be smaller than 1/10 of this. Number 2, the conductor has to be protected, so you have to put them in a conduit, some type of a conduit. Number 3, the conductors have to land on one or multiple circuit breakers here that limit the current coming out of this conductor to the ampacity of this conductor. For example, number 10 can give me only 30 amps, so I have to go limit this to 30 amps. These are the 3 conditions for using the 10-foot tab rule. Any comments, guys, about the 10-foot tab rule right here?
That could be 215.
Huh?
That could be 215 amp breakers.
2 15 amp breakers, yes. Yes, that could be 2 breakers or 3 breakers, 10, 10, 10. Good point. That circuit breaker can be 3 breakers, 10, 10, 10 each, or 1 breaker, 30 amps. As long as you limit it to the ampacity of the conductor. Good point. Or fused. Now, moving into the circuit breaker, moving into the 30, now this is the 25 feet. Let's take a different color for the 25 feet. Everything in blue sucks. Okay, so let's say, now this conductor here, how's this color? That's not bad. For the 25, the code says, guys, cannot be less than 1/3 of the overcurrent protection device. What's the overcurrent protection device? 300. What's 1/3 of 300? 100. Can you guys go do me a favor? Size me a conductor 100 based on the 75 column. That will be because number 3 in the 75 column. Number 3. So that will give me number 3. So, and then number 3, how much current number 3 can give me under 75 column? 100. So then you have to put, what do you need to put here? 100 amp. So I can't pull, the smallest conductor is going to be number 3. It's landing 100 amp to limit the current that you're pulling to 100 amp, otherwise you exceed that basic conductor. You have to put these in a conduit to protect the conductors. You have to land this conductor in an overcurrent protection device. Use your circuit breaker to limit it to 100. By the way, this 100 could be, well, this could be, could I land this in the main lugs only?
Less than 6 breakers, 6 or less breakers.
But the break, so typically we feed it, but it has to land in a circuit breaker that adds up to that density. So technically, I have my disconnect here for the system. So if I want to shut down this, I can shut down, okay, I'm not going to go there. So it's a 100 amp panel, I can't put more than 100 amp. But I can split these, say, into 3 or 4, 100 divided by 4, 25. I can split these into 4 25 amp circuit breakers in a panel. And that's okay.
You could also put the 30 amp breaker there and just have to use the number 3 wires.
Yes.
Based
Yeah.
on that 300.
Yes.
That
Yeah.
could be a 10 amp.
Yeah. Oh,
But you
yeah.
have to use the number 3 wire.
This is max. The amp here is the max. The max.
What you're really doing, what the rules really saying though, is the wire.
The wire is what governs.
You can't go any smaller on the wire.
So number 3 is the smallest I can do, and if you put number 3 here, you cannot put more than 100 amp here. I can put 90, 30, 40, any amps I want here. Yeah, the max. Any comments, guys, about the 10-foot tab rule and the 25-foot tab rule? A lot of people take advantage of it, guys. You take a feeder, a 400 amp feeder, put it along the wall in your manufacturing floor, in a gutter, and you tap 10 foot with the fuse disconnect and feed machine 1, machine 2, machine 3, machine 4. You save you an MCC. It saves you a motor control center, a panel. Right? So there's a lot of advantage for it. What's the disadvantage? Any ground fault or short circuit here on the line side of all these equipment could easily trip your main.
The 25-foot has to be in conduit also. Right?
Yes, yeah. Full protection, so you have to protect them in a conduit, the 25 as well as the 10. Put them in a conduit.
I think your code even says metal.
Yes, I believe metal conduits to protect them from physical damage. Not less than, I think it says it here, the tap conductors are in a raceway which shall extend from the tap to the enclosure. I don't know if it says for field installation with a tap, blah, blah, blah. Okay, the device on the, okay, so I don't know. Check, I can't remember the language, but it has to be in a conduit, typically EMT conduit. Typically EMT conduit, yes sir.
If that 100 amp is a panel, can you come off of that and
Yes.
use the tap rule again?
No, you can't tap a tap. You can't tap a tap. The code says you cannot tap a tap. You tap once,
You're done.
you can't tap a tap.
So if that's a panel board and you stick breakers in there, anything coming off those breakers is a branch circuit. at that
Yes.
point.
Oh yeah, I can come here. That's not a tap. I can take from here 30 amps here and feed this and this a load conductor number 10 here. Right? No problem.
But you couldn't make that a tap.
No.
Circuit off that breaker.
No, you can't tap a tap. It's already tapped. Okay. Any comments, guys? Any questions? Okay, so that's that 10-foot tab. 10 foot and 25 feet tab is the same thing. You see? Okay, please. So here's how you do it, guys. So in a case like this, if this is 100, your main circuit breaker coming in here, guys, if this is 100 and this is 100, what would this be to meet the code, the maximum? This can be 10 times 100. This can be 1,000 amp maximum here, right? You guys see why? There's 100 amp here times 10. If these are 10 foot, let's just say, oh, I should have said that. If these are 10-foot rule, the 10-foot rule, this is a 10-foot rule. I'm taking it 10 feet. Let's just say this is 25 foot. 25. Okay, 25, 3 times, to tap 200 amp, how much this circuit breaker has to be? 600, right? So which one is going to rule then? 25. The 25 is going to rule, so that cannot be 2,000 then. It has to be 600. Can you guys see that? So I have it to take a 600 amp here, tap it with 1/3, give me 200, and then tap it with 1/10 of 600 is what? 60. So 60 amp. The smallest that I can tap. The smallest that I can tap. But I'm tapping 100. It's okay. No, there's no problem with that. I can size my feeder for 100 now. That's okay. So the minimum that you can tap here is 60. The minimum conductor that you can tap is 60. Can I tap 100 conductor amp? Yeah, no problem. What's the decisive factor in, oh, how about if 1,000, Chad? I keep going up, right? What's the decisive factor here? Well, when you do this, or when you design a system, you have to add all your loads and make sure that feeder here can handle it, right? To start with. You know, so your feeder from the top here has to be able to handle all these loads. Then you start sizing your conductors. So that's your tabs. Any comments, guys? Any questions about the tabs? Tabs. So that's your tab. So we got our tabs, overcurrent protection device. You can see how as you move, you have to put in a conduit, 25 feet, land, beautifully put in a circuit breaker. And that's what tab is. That's what your tab is. By the way, who said, can you tab a tab? Did you say that? Well, as a matter of fact, a tab is coming here. So let me say, I'm going to go put another junction box here and tab this feeder. That's what a tab, right? That's tab. Now, if I come out of here, look how this is come out of here and tab this. Is this tab? No. This is not tab because it has an overcurrent protection device here. That's a whole completely different animal. Tab is coming from here.
Use the tap rule on that little.
Yes. Yes, now we can tab again here. Yes. As long as you, now, as far as this tab concerned, this doesn't exist. Because you're protecting it, this conductor is protecting, this is like 100 amp, you have your full protection here, you can continue tapping again. But tab is, here's the tab conductor, this is the tab, I can't tap this tab. Anybody have done that? Typically, I've never seen it where you go here, circuit breaker, come here, tab again, but you wouldn't do that. But you can though. So the top.
Well, what I was thinking, I've seen it in control panels where they come into a control panel running a machine, and they've got a 100 amp breaker on it. The first thing they do is go to distribution blocks, and they're pulling little number 14s off of it and going to fuses, operating various pieces of equipment in that control panel.
Now, let's go back to this, to tab rule number 1. Now we were talking about the control. For field installation, where the tab conductors have leave the enclosure or the valve, the tab is 10 feet for field installation. If you're tabbing conductors for control inside a box, then your conductors can be smaller than 1/10, but they don't leave the box. Do you know what I mean? They're not leaving. They're going nowhere. So what you're doing here basically is you're tabbing here and you're staying doing control and whatever you're doing here. These conductors, the tab conductors, have not leaving. They're not leaving the enclosure. Then you can even go less than 110, and that's what you're dealing with.
Because the fuse on the end of that little tab is protecting that short length.
But think about it. If you're in an enclosure, I mean, do you go 10 feet, more than 10 feet inside an enclosure? It gotta be a big enclosure to go 10 feet inside an enclosure, which it could be a control enclosure. So if the tab conductor stays inside the tab, inside the enclosure, you really have no limitation on what size of conductor you can tap. Does that make sense?
You tap another height
Inside the enclosure. Yep.
and because it ends in a fuse, it protects the fire.
And you can land it on a fuse. Yeah, you can tap it and land it in a fuse circuit. Yeah, that protects the control circuit. Or there's there's also exception where you don't even have to put a fuse. Remember when we talked about, there's there's a few exceptions where you don't even need a fuse. Any comments, guys? Any questions about that? Tabbing the tabs.
Yeah, industrial, place two for 25 feet.
Industrial?
Industrial.
But yeah, industrial have its own limitation though. If it's non-industrial, it has a couple of other rules. So tab, okay, 25. Okay, so let's talk about transformer tabs, shall we? Transformer tabs. There are two types of Any question, guys, about the 10-foot tab without transformers? Let me talk about transformer tabs. Transformer tabs, guys. If there's a couple of transformer tabs that's really interesting. Tab, transformer, primary plus secondary, not over 25. Okay, let's go to tabs over 25 feet. Okay, transformer secondary conductors. Transformer secondary conductors not over 10 feet. Let's go to the first one. Tab, supplying transformers, primary and secondary, not over 10 feet. So this is the transformer tabs, guys, is really interesting. You're looking at a circuit breaker coming in here, right? That's what we take out transformer here. Now, the first tab that I'm going to talk about is the tab right here. How far? Because this is a tab, right? From here to here, there's no overcurrent protection device. From here to here, no overcurrent protection device. If this is, let's talk about the secondary conductors. Secondary conductors 10 feet. Let's say this is 10 feet or more. Can you guys with me? 10 feet or more. So the secondary conductors are 10 feet or more. Okay. Now, what size conductor for 10 feet or more? What size minimum size conductor that I need right here for 10-foot tab? The reason why I say this 10 foot because do you see any circuit breaker here? Nothing whatsoever. The first circuit breaker is sitting where? Right here. Okay. So how far? What's the smallest conductor that I can tab out of this transformer without an overcurrent protection device? Number one, guys, the code says when you tab them, the rules for these, we talked about them. The secondary conductors do not extend beyond the switch gear, enclosure, flows in a raceway which extends from the transformer to the enclosure. So you have to put them in a raceway, land them in a circuit breaker, and here the size that they size it, guys. That conductor cannot be. Let me go put a different color here. That conductor. Okay, let's take this one 480, shall we? This is a 480 transformer. Typically, I need somebody to do the math though. This is 480, and this side is 208. Very typical. Okay. So the smallest conductor that I can use is 1/10. Can you guys see that? 1/10. Shall we give me an overcurrent protection device? Shall we use 300 amp here, just for the heck of it? 300 amp on the primary side. 300 amp. So we're going to tap this 300 amp. On the primary side, 1/10 of 480 divided by 208. Now we're going to take the voltage ratio in consideration, multiplied by 200, 300. That's the smallest conductor that you can pull here. Okay, what's 480 divided by 208? So if you take my 480 divided by 208 equal 2.3, multiply it by 300 equal 600. Did they do it right? 600. Okay, divide by 10. There's still 10 there. Equals 69. So did I do my math right? 69.2. 69.2 is the smallest conductor that you can tab for 10 feet out of this transformer if your overcurrent protection device here is what? Is 300. If your overcurrent protection device here is 300 for 10 feet. Okay, so 69, what's the conductor size 69 based on 75 logs? 69, would that be number 6? Number 6. So the smallest, again, smallest conductor is number 6. So the smallest conductor here is the number 6. What's the number 6? How much current number 6 can carry, guys, under number 6 wire under amp? Oh, it doesn't say that. How much conductor can number 6 carry under 75-degree column? How much? 70. Then this circuit breaker cannot be more than what? 70 amps. That's the smallest wire and the smallest wire and the largest overcurrent protection device that can land the number 6 on it. That's your 10-foot rule for transformer. 10-foot rule for transformer. I'm not saying that's how we size it. I'm saying that's the smallest wire that you can tap out of this transformer for 10 feet. Now, if your conductor can be 4 here, we're good. You see what I mean? But that's the smallest wire that you can tap out of this circuit breaker under these circumstances. Am I clear about the smallest, guys? Typically here in a size like this would be 4 the conductor, so we don't even worry about this. So that's, and we can have multiple taps from here. You can have another tap on the secondary side. The 25-foot tap, though, it has to be in an industrial installation secondary conductors. Only if it's in industrial, they allow you, for industrial application, they allow you to go up to 25 feet here. 25 feet away from the transformer. Other than industrial, you have to stick with the 10-foot. Stick with the 10-foot. Okay, now that's if you have a 10-foot tab on the secondary side of a transformer. I don't know, guys, how many of you, there's also a rule that says the primary plus secondary conductor. So I'm going to use this one. From here, can you guys see that? From here plus from here. The distance is from this panel to this panel cannot be more than 25 feet. Okay, from cable coming in, cable coming out, all of them cannot be more than 25 feet. There's a rule tab for it. The tab rules for it, when both of them tab supplying transformer primary plus secondary, not over 25. Here's what the rule for this. The rule for this conductor cannot be less than 1/3, the conductor here, 1/3 of the 300. What's 1/3 of 300? 100. So this conductor, when you size it, has to be number, what did we say 100 would be number 3? Can anybody tell me why the heck would the overcurrent protection device be 300 and the conductor 3? Inrush on the transformer. Right? The inrush on your transformer could take this overcurrent protection device. Typically, if it's a circuit breaker, we can go to 2.5. So that's the minimum, 3. On this side, Now on this side, look at the minimum again, minimum. On this side, same thing as you take a 1/3, but now we are going to the secondary side, so you have to multiply by the voltage, which is 480 divided by 208, right? Multiplied by 300. So you have to kind of adjust it to the voltage. So if you take 480 divided by 208 equal multiplied by 300 equal divide by 3. That's a third. This conductor cannot be smaller than, in a case like this, cannot be smaller than 231 amps. Cannot be smaller than 231. Now we start to make something substantial. Cannot be smaller than 231 amps. What would that be? 4 watt? 250 MCM. So that conductor, under these circumstances, cannot be more than 250 KCM. Thank you. You're going to get extra credit for next year for answering. So what I did, guys, here, there are 2 tabs. Rule tab number 1, if the primary and the secondary together are less than 25 feet. That's one rule tab. So this has to be number 3, cannot be less than number 3. This cannot be less than number 250. Check, rule number 1. Rule number 2, I don't care about the primary. The primary has been sized to match the overcurrent protection device. Did you guys hear me? The primary here has been sized to match the overcurrent protection device, like 300 amp. On the secondary side, I care about from here to here. That only give you a 10-foot rule. If you are from here to here, the minimum that you can pull is what? Number 6. The minimum that you can pull is number 6. You can see that these are 2 tab rules. And if you think, if you're doubting Thomas, it's all in page 93, and I expect you guys to review them tonight. As you go home, each and every one of them.
What are you measuring 10 foot and 25 foot in? The conductor length?
The conductor length, from here to here.
All the way to the connection point.
All the way to the terminals.
So your conduit actually is shorter than that.
Your conduits will be shorter than it, yeah. Because you're measuring to the termination. The conductors, what you're tapping is not the conduits. So in a case like this, in order to tie here, you can have at least 2 feet or 1.5 feet to tie from each side here, right? Now don't you need at least 6 inches here, or at least a foot to tie your equipment? So it could be short. It could be 8 feet between them. This is typical. A system like this, guys, the transformer will be literally sitting here, the high voltage panel here, and the low voltage panel right next to it. And they are within 6 feet of each other. That's what we use this system. That's how you tab to feed a transformer. Tabbing to feed a transformer. Now, there's another tab, that 25-foot tab for the secondary. You see that 10-foot tab? I can make it 25 with no limitation how small the conductor is, as long as it's protected from physical damage, landing on an overcurrent protection device that protects the conductor. And that 25 feet has to be in an industrial, they call it industrial installation. So qualified people like yourself will only maintain these systems. So that's manufacturing. If you have manufacturing, they allow you to actually tap from a secondary transformer, go 25 feet before you put your circuit breaker from the secondary of the transformer. Rules are only for the manufacturing. How about this is inside the building? How about if you're outside the building? Have you ever thought, guys, on farms and all the stuff, tapping a conductor right on the top of the pole? How do you do tabs there? Do you put overcurrent protection device all over? Inside the building, these are the rules. Outside the building, the only rule is you can tab and go as far as you want. You're outside the building. If you Arkansas bark, you're not going to burn Mother Earth. Hopefully not. You're on the top of the pole or underground outside the building. Tab as long as you want. The only condition is, as you tab the conductor, so I'm outside, I'm going to tab I'm going outside here. Here's my overcurrent protection device. I'm making a network, feeding here, and feeding a load here, and feeding another load here from that pole, feeding a third power here. The only condition, guys, is to protect, if this conductor is 100 amp, this it has to land in an overcurrent protection device that's 100 amp. So whatever your conductor that you tap for a mile, and I'm exaggerating here, a mile, from here to here is a mile, as long as the conductor is 100 amp and you landed 100 amp at the end of it, the code is okay with this. That's where utilities goes into tabbing, not like we apply to utilities, but you can tab overhead, and as long as you protect them, they land in an overcurrent protection device. So the conductor they have to be protected from physical damage in an approved manner. It doesn't say a conduit. Approved manner could be on the top of the pole. That's protection. And the conductors terminate in a single breaker or single circuit breaker that limits the load to the capacity of the conductor. Made to supply the number of additional overcurrent protection devices. The overcurrent protection device for the conductor is an integral part of the disconnect. The disconnect means the conductor is installed in a readily accessible location outside of the building. So as long as all this mess is outside the building, go tab as many as you want. Does that make sense? That comes handy if you're doing farms and going the service conductors in the pole and tabbing from them. As long as you tie number 10 with 30 amp at the end of it, we don't care. If you burn it, it's outside, right? Why do you think the code cares about tabbing the conductors inside? You can burn the building. Any comments, guys, about tabbing outside? Outside meaning underground or outside, as long as you're inside the building. Okay, so we got that one. Okay, secondary conductor is not over 25 feet. The ambiguity, okay. Now, if these, okay, so this is secondary conductor is not over 25 feet long. They go 1/3. Now, the last tab, guys, is that yellow one here. They allow you to make this one 25 feet too. If this conductor is 25 feet, then it becomes 1/3. Only that conductor of the same thing, 1/3 of 480 divided by 208 multiplied by 300, which is, we already sized it, 300. So which equal, what did we say? Equal 231 amp, which in turn equal 250 kcm, 250 kcm. 250 kcm. So what's the difference between this and this 250? This 250, guys, is the length from here to here plus the length from here to here is 25. This tab, the length from here to this equipment is 25. So they give you a lot of leeway. So can you guys see? I mean, I can go from this transformer 25 feet if I size my conductor to 50 kcm. Now, if I want to go 25 feet in an industrial supervised location, no limitation, no overcurrent protection device, no minimum. They're 25 feet, but that conductor doesn't have to be even 250. So to summarize, guys, there's one rule. If you tap the secondary only for 10 feet, if you tap the secondary only for 25 feet, there's another rule. If you tap the secondary and the primary for 25 feet, not 10 in this case. It doesn't make sense, 10 primary, secondary, right? Not a whole lot of juice, not a whole lot of length. 25 feet, primary plus secondary. You can see the rules. And the last rule, guys, if you're tabbing outside the building, the limit is the sky. You can tab and go anywhere you want. So these are the tab rules. Unlimited. Unlimited. So this is another tab also, guys. So if you have a transformer here, and here's my conductor coming out of transformer, and I'm going to tap this, we're outside. Back to the outside. I'm tapping that transformer side. This is my secondary side of a transformer, this area here, and I'm tabbing it. How far can I tab the secondary side of the transformer? Basically, this application here, except outside. No limitation. If you have a transformer outside, and you tap the secondary, take it from the secondary side, go 300 feet, 100 feet, 200, whatever. The only condition at the end here, you have to land a circuit breaker or a fuse that protect the conductor at its own ampacity. So they're so relaxed when it comes to outside tapping a secondary of the conductor or a feeder. Very relaxed. Any comments, guys? Any questions? These are the tab rules of the conductors. The tab rules on the secondary of the conductors. The secondary of the conductor. Any comments? Does it make sense? No? You guys tab a 482 low voltage, guys. You're laughing at me there. Sorry, guys. Thank you. It does make sense to me sometimes. I don't know. Any comments, guys? All these, as an engineer, a lot of engineers don't like the tab rules. The tab rules is compromising the integrity of the power system. Every time you tab a conductor, you compromise the integrity of the power system, right? But they're cheap and they work. So if your system reliability is not an issue, a manufacturer who's making shoes or whatever, they don't care too much about what interruption the product. So that could be an easy fix for them. And you know the NEC code book is the common denominator between 300 million Americans and 50 states, right? Common denominator from Mississippi to Minnesota. Common denominator is what? It's always the lowest common denominator. Okay, so these are the tabs I'm going to talk about, guys. Anybody has any questions about the tabs? We talked about all these tabs of the transformers. Secondary, we talked about all the secondary tabs of the transformers. A 10-foot tab. Landing them. When you go to the transformer, guys, this is a good rule. 25 feet, here's a 25 feet rule. You have to land them into the 6 disconnect means. You can land them into as long you parallel. Here's a parallel set. Secondary conductor basically is not less than the transformer secondary current, and the sum of the overcurrent protection devices does not exceed the secondary conductor ampacity in an industrial installation. So no limitation on how or the size of the conductor. No limitation on the size of the conductor. The ampacity is not less than the transformer secondary current rating. Yeah, I mean, you can't put here 100 amp when the transformer can only pump 10 amps. You know, you still have to look at how much current you can pump out of that guy. So, conductor, secondary conductors, we talk about these. Okay, so that's basically 10 times. Any comments about sizing the secondary of the transformer? Secondary transformer. I do have something I'm going to show you when it comes to transformers, guys, and sizing them. The NEC code book, when it comes to the transformer, says that okay, so let's go right here and go to fuse. Okay, here's a coordination study done for a transformer. Let me come here and click on it and maybe expand it a little bit. There you go. Okay, so here's an overcurrent protection device, guys. My feeder, talk about overcurrent protection device. My feeder here is a 1200 amp feeder, and that's a feeder. Then I have a circuit breaker right here. See this sitting on it? Then I have a circuit breaker primary of the transformer. That's to protect the primary of the transformer, sitting at 60 amps. 60 amps fuse, 600, yeah, 60 amp fuse. It's a fuse, and that's the primary side. The secondary side is a circuit breaker, 100 amp circuit breaker, and they are protecting, where's my transformer? They're protecting a transformer, 30 kVA transformer. I have a 30 kVA transformer, 60 amp fuse on the primary. On the secondary side is 100 amp. And you can clearly look, if you know how to interpret this, you can clearly see that the damage curve, I don't know if you guys can see that black wire, two sides of damage curve. So I'm allowing, I want you guys to look at the inrush here. If you look at this, click here, Chad. There you go. Can you guys see that black curve and that red X here? This one here is the inrush of the transformer. So my fuse is allowing my transformer to start. If I move this one here, every time you start, because of inrush of a transformer, your circuit breaker is going to trip. What I like to mention here when it goes to this is you always, if you can coordinate, you can always get smaller fuses or circuit breakers than what the code allows you to do. And just a quick reminder, why do we care about smaller circuit breakers and fuses? Because smaller circuit breakers and fuses will get you better arc flash and protection. Smaller arc flash category and better protection as you work on these equipment integers. So that's using a fuse here. And I don't know what type of fuse we use. We use on the fuse type. There you go. So we're using a 600 LPJ60SP 60 amp LPJ fuse. The fuse, and I don't know the manufacturer. Busman. Thank you, Busman. It's a Busman fuse. Those guys, and they did not pay me to use their product. Okay, so that's what we do when it comes to sizing circuit breaker fuses. Okay, so we're done with the fuses, guys. Jeff yesterday talked about sizing fuses and circuit breakers for motors, so you know how to size them. 2.5 or 1.75 or 300, depending upon inverse type circuit breakers, or dual element time delay fuse, or non-time delay fuse. And the reason why we pump the circuit breakers up because of inrush of motors. Same thing for transformers. Transformers are to be sized. The primary is 2.5. For example, if the primary of your transformer is 100 amp, my overcurrent protection device can be as high as 250 amp, as high. Why do they do that? Because of the inrush of the transformers on the primary side. Most of us engineers like to size them based on 1.25. Why? Because lower short circuit breaker will give you better protection. But to check for ourselves, though, you can go and run these analyses, and if the circuit breaker acts as it says it will act, back to you, Al, right? So when that curve, you're looking at beautiful curve, I'm assuming that the manufacturer of the circuit breaker have followed you, Al, which they do. And if the manufacturer of the software also inputted the data right, look how many Fs. And if the engineer like Chad was not drunk when he was coordinating it, if all the if these Fs line up, then a 1.25 will protect you. But if you don't know, then a lot of people don't know and they don't want to take these Fs, so they go the largest overcurrent protection device and cover your butt type design. So you can go from an 100 amp circuit, in 100 amp transformer, you can either put 125 amp fuse on the primary side or 250 amp fuse. Look at that range between them. So I tend to go lower than 250 just for protection, but then I run the analysis on it. Okay, batteries. Overcurrent protection device shall be permitted to be installed. Okay, now for batteries, do you guys do data centers? You do data centers. What type of business? Are you guys running a data center or what? Okay, so data centers, may I ask who the money employee? Target, which one? Brooklyn Park, cool. Do you know that I worked on Target? Or did you guys burn the feeder for you? Did we burn one? Did I? So we, what happened to that feeder? I can't talk because there's litigation going on. So I can't talk about it, but you don't have to. We're record. But I know one of our engineers involved in it right now, right? Is that what you guys going? So I can't talk when when recording. But I want to tell you this for the record, one thing. When a feeder burns, guys, there's multiple things that could happen in a feeder. Multiple things could happen in the feeder. So, but that was a high profile. Is that the job that you said? The generators? Yeah. And that was the feeder that are going to the data centers, right?
Yes, that was
The UPS. Yeah, yeah. Okay, so when you have a data center like this one, you can't put the circuit breaker right at the point where they receive the power. I mean, this is hazardous. This has a dislocation right in here. So they allow you, instead of putting it right in here where they receive the power, they allow you to put it further away, as they call it, as close as practical to the storage battery terminals in a non-hazardous location. So typically what we do is we pull them, and we did them, a few of them. We pull these cables from here, we go closer, far away from this area on the wall, and we throw our disconnect, DC disconnect there. Any comments, guys? Any questions about that? That's another exception where the overcurrent protection device does not have to be exactly where the conductors, where do the conductors receive power here? Right here. They receive power, and they pump power, right? Because you're pumping power into these, storing your power. And when you lose your UPS, when you lose your power, you're pumping the power back into UPS 750 kVA UPS, right, into your data center. 660, I want to say, something in the 600 volt, at least typical. I don't know how much do you guys, I can't remember what the voltage is. 530, something, yeah, something around the 600 DC, yeah. That goes into the UPS, and from the UPS, it will convert it into AC and dump it across the PDUs. They call them PDUs, power distribution units, that feed the racks, your racks that you're talking about.
So a charging system is continuously charging these batteries.
Yes.
And if you lose your utility power, well, it's constantly drawing off this anyway, so you don't even get a bump.
Yes, that's the whole idea of UPS. You don't see any interruption, because at the DC level, you're tying your grid with your UPS. You're paralleling. Do you guys remember the concept paralleling? Except at the DC level, you don't need to parallel. If you have a 9-volt battery and a 9-volt battery, I can tie them together without worrying about the frequency. There is no frequency. So if you have, if your UPS production is 550 and your battery's production is 550, you can tie them together, and they're at all time constantly tied together. They're just charging the batteries every time it discharges, charge the batteries, and you draw the power through the UPS this way. The minute the power gets interrupted from the side, you're no switching mechanism whatsoever. You just flip the power. You start taking power from the batteries.
You're paralleling this and the UPS? Is that what you said? You're paralleling?
You're inside the UPS, you're paralleling this source of power, the battery source of power, and the utility source of power, and the generators, if any. All these are paralleled inside the UPS at the DC level. Because the UPS has an AC level and DC level. At the CC level, when you take the AC, convert it to DC, you tie your battery, then you invert it back to AC at the right frequency, 208 and 120, and right voltage and frequency. It's a really unique system. The problem is high profile, and they have a lot of maintenance, high maintenance on them. High maintenance. Okay, location in or on premises. The location, guys. Overcurrent protection device. Overcurrent protection device have to be readily accessible. For short people like Chad, they want them 6'7", so we can reach the top of that circuit breaker and get it. There's some exceptions for this one. For example, supplementary overcurrent protection device. So I decided to fuse this light. Does it have to be, or circuit breaker to this light? Supplemental. Does it have to be 6-7? No. Goes supplemental. Busways, your busway is set at 25 feet above the manufacturing floor. You know, you can have other means of reaching these disconnects, the sticks and so forth. So there's a few exceptions for the overcurrent protection device. Utilization equipment, your air handling unit is sitting in the magazine. As long as that circuit breaker next to the air handling unit, that mezzanine is okay. So these are few, otherwise it has to be really accessible 6-7. Occupancy, each occupant shall have really access to all overcurrent protection devices. Service and feeder occupancies where electric service under building management, continuous management at all times, then you don't have to have them access to the overcurrent protection device. For example, hotels and motels, you know, they don't have to give you access to your circuit breaker that feeds your room or your suite because they're under continuous management. If something is to happen, you can call that management and they'll come and turn the circuit breaker for you. On the other hand, guest rooms, suites, multiple occupancy buildings. On the other hand, if you have an apartment building, they have to give you access to the branch circuits that feed the apartment, right? Not the feeder, but the branch circuit. So in your apartment, you will have access to your load center, so you can have control over them. So branch circuit devices, maintenance will provide the building management where there are under direct supervision. You don't have to do that. Okay, a couple of other things that we need to do. Not exposed to physical damage. Your circuit breakers, you can't put them in a place where you can run with a fork right through them. That's why you find in manufacturing floors when they have panels, they have these, what do you call these support, what do you call them? Guards, yeah, right around them because a fork can run into the MCC, which is sitting right there. Not in vicinity of easily ignitable material, so your clothes closet, you can't put a fuse disconnect right through it because any arcane spark will ignite the surrounding. Bathrooms, believe it or not, you can't put them in a dwelling units and guest rooms and suite bathrooms. What it doesn't say here is you cannot put them in a commercial bathroom. It's only dwellings, guest rooms, and guest suites, and hotels and motels. But if, other than these, you go to a commercial building, you can put your panel in a bathroom. Have you ever seen a panel in the commercial building and bathroom? The reason why they restrict these guys is because if you have a commercial building, office building, it's engineered most likely, and you will never see a panel inside a bathroom or commercial building. No, not located over steps. That came in 2005 or 8, I want 8, because we're just tired of people tripping their. So if you want to put a fuse disconnect or circuit breaker, violation of the code here, it has to be on a landing. Anybody knows why? Because it has to be readily accessible and clearances in front of the equipment to work on it, and that place is not, it's not proper place to work on, right? So it has to be in a landing. So that came in 2000 some. Circuit breakers, guys, also have to have a directory that indicate which circuit is feeding which. And if you have a spare, it should say spare. If you have a spare circuit breakers, and you shouldn't say Chad Kirby's office because he could be fired tomorrow, and nobody after a couple of years know who Chad Kirby is. So it has to be. It came in 2008. They said it can't be transient name, it has to be a solid name. You know, a name red or whatever, room 114. Operating handle shall be permitted to be accessible without opening the door or the cover, turning on and off for the breaker handling. Vertical position, enclosure of protection device shall be mounted in a vertical position unless there is shown to be impractical. Anybody have installed the fuse sideways, this way, or a panel? I heard in Canada they install them this way instead of vertical. It's not against the code, but you have to prove it's impractical. So that's a couple of things we can handle. Disconnect means for fuses. A couple of things, guys, about fuses. Cartridge fuses and circuits of any voltages were accessible to other than qualified people, and all fuses in circuits over 150 to ground. 150 to ground, I'll give you 277, 480, right? Shall be provided with a disconnect means on their supply side so that each circuit containing fuses can be independently disconnected from the source of power. So any fuse that accessible to non-qualified people, and it becomes a rule for us for any fuse 48277, 600 volt fuses, not 208, then you have to have some type of a disconnect to disconnect the fuse from the circuit, or changing and so forth. Fuse circuit breakers, when they operate, shall not be burned or otherwise injured by their operation. There are 4,000 amp circuit breakers, guys, and fuse switches and handles on them, that if that circuit breaker is with a trip and you are there, and it could slam you in the head and give you a really good good hit here. So it has to be placed in a place where if it operates, it's not going to injure anybody. Couple of things about fuses. These are your 120. If you the plug-in type fuses are limited to 120, 30 amp, 15, 20, and 30 amp. You guys use them? Not a whole lot. We're changing the fuse panels into a circuit breaker panels right now, right? In dwellings. Replacement only. You have to replacement only if there is no overfusing and tampering. You're not putting pins in the back of it so it doesn't trip forever. So that's your plug type of fuses, and it has to be limited to, again, it accepts 15, 20, and 30 amp fuses, and no over at the S type, amp rating with the S type, so you cannot put a 20 amp fuse in a place where a 15 amp fuse should be. So you overfuse it. That's your S type, limit you. If it's number 14, 15 amp fuse, it will be limited. You cannot put a 20 or 30 amp fuse in, and so forth. Okay, so here's the S type fuses take you from 0 to 15, 16 to 20, and 21 to 30. If you guys remember, this will be 14, this will be 12, and this will be 30 amp. And you cannot put a 30 amp fuse in a place where a type S fuse 15 should be. Right? Makes sense with these fuses. Then you move into maximum voltage for fuses. There's 300 volt type cartridge fuses. This has the same, the name says you cannot, this is rated for 300. So the fuse and the fuse holder are rated for 300, not over 300. Single phase, here's where you can use these. Single phase line to neutral circuit from a 3-phase 4-wire solidly grounded system. Line to neutral does not exceed 300 volt. Line to neutral does not exceed 300 volt. So that will cover almost all the voltages that we use: 208, 120, 240, 120, and 480. Well, 480 here, it wouldn't get you 480 because of the limitation of the voltage here. But 208, 120, 240, 120, and that's about it. Non-interchangeable, they go from 0 to 600. You shall not put a fuse with a higher amp in a fuse holder with a lower amp, or a fuse with a higher voltage with a lower voltage in a fuse holder with a higher voltage. Right? So you have to match the fuse holder to the fuse amp-wise and voltage-wise. Amp-wise and voltage-wise. Huh?
It's 700.
700.
They look like 3 frames ago. They look like those guys there.
Yeah. So there's so many. When it comes to the fuses, guys, I don't know if you use fuses all the time. I don't use a lot of fuses. So fuses right here. Tons of application for all the fuses that you can use. I don't claim to know all of these. There's different type of fuses. Marking on the fuse. A couple of things. You have to have the amp voltage. If you're interrupting rating other than 10, they always test you in master and general on that. Other than 10, you have to label it like 35K, 200, 2000K. If it's current limit fuses, we need to know about that, and we need the name or the trade or the manufacturer so we can sue them if it doesn't work. Shall not be required to if you have interrupting rating, shall not be required on a fuse is used for supplementary protection. So if you have a fuse for your air handling unit sized by the manufacturer inside the air handling unit, a supplementally might not have rating in it. but it will be your listed though and so forth. Classification. Fuses, fuse holders shall be classified according to voltage and current. As it says, fuses rated 600 volt nominal or less shall be permitted to be used for voltages at or below their voltages. 600 volt fuse, I can use it to a 240, 480 system. I can't use a 600 volt fuse on a 13K fuse in a 13K system, 13.8K. Classes of fuses. When it comes to classes of fuses, guys, notoriously famous RK5, current limiting fuses, RK1. So there's all these, and I personally, if I'm to be encountered the field fuse, if you forget about what they use for, those guys put a great application guide or which fuse fits your application better. As in, set of fuses are great for motors. Another set of fuses are great in terms of the class. Another great fuses, I think also are great for feeders. So they have really good tables that classify which fuse is rated for which. Technically, dual element time delay fuses, we use them in motors a lot. It provides a backup for your overload with the time delay, and with the time delay allow you the inrush, allow you to size your circuit breaker, your fuse lower. For example, 100 amp circuit breaker can be sized at 175 amp fuse, versus if it's non-time delay fuse, you have to size it at 300. So give you a smaller size, and then remember, every time the fuse is smaller, the arc blast is smaller, your chances of surviving and going home to your family is higher if you are to work on these equipment energized. They distinguish between non-current limit fuses and current limit fuses, guys. A current limit fuses, if you put a 35K into this fuse, what comes out of it might go from 35 down to 25. Great application for if your equipment here is rated, you bought a piece of equipment from China. This piece of equipment, let me say if it's, I'm going to fuse my equipment here into coming out of here into, let's see, my piece of equipment coming here, tying it. This is rated for 25K with stand rating, okay? And right here at the load side, I did the short circuit calculation. I came up with 35 kilo amp. Now current, if it goes, as it goes through the circuit, the fuse, guys, it will open so fast that within a quarter of a cycle, that 35 will never be seen by this equipment. Who cares? After you have a short circuit, three-phase, highest short circuit could be encountered in this piece of equipment. The only thing that's going to be seen, the 35 will open enough that it will not see more than 25. And there's a couple of tables that you can size current limiting fuses. Here's a great application of current limiting fuses. How many of you guys have seen this? Raise of hand. No? Or is it too late now to think, Chad? Look at this. This is right here at this point. It is what they call the RMS value. The RMS value right here, guys, the average value is 86,000 amp at this point. If I have a current limiting fuses, so it goes all the way up. Can you guys see that? It goes all the way up. Then it goes across until you hit that B and line, and it then drops it down. That's how much you drop it down. It will drop it down to here. Dropping it down to here means taking this 86 and making it only 21. So now imagine this equipment that should have been rated for 86,000 withstand rating. Now it only needs to be rated for 21. Who cares? Your equipment will survive a short circuit condition. That's the baking. Now the shaking, guys, is, look at the shaking. The peak is always responsible for the shaking. It will drop your shaking from 198 down to 49. How does it do that? It continues here. If you don't have it, here's what your shaking would be. If you have it, you continue in this path and drop it from here to here, right? As it did drop this one from here to here. So long story short, after your short circuit incidents, your equipment will be shakerless and breakerless. So you survive, your equipment will survive the short circuit condition. And arc flash, when we run arc flash analysis, guys, on the system, it can take you, this category can take you from category 4 all the way to category 1. Just by putting a current limit fuse. Any comments, any questions about current limit fuses? So if you have a situation where you need to, limit the current limiting, in your system, a current limit fuse will be your baby. Any comments? You know what they do on the utility side? On the utility side, they use fuses that when the current goes right through them, or it turns into insulation if it's too high. It chokes the current on the utility side to choke the current. And the low voltage side, what we do is we open the circuit breaker fast enough. Or the fuse circuit breaker. Here's a table, guys, that can get you from manufacturer fuses, get you multiple current limit fuses that you can size for different services. Then there's a couple of fuses, guys. This is all from Bussmann, and feel free to look at them. Branch circuit fuse, fast-acting branch circuit fuses, the class that they come. This is and all the amps that they come within, the voltages that they're rated for, and the interrupting rating. Look at that. It's so easy to get 200,000 RMS rating on a fuse versus circuit breaker. I don't know if they make more than 85K interrupting. I believe if you go larger than 85K on a circuit breaker, they start fusing the circuit breaker. So they can get, it's easy to throw a small fuse like this, and look how much current that fuse can handle. So it's really easy, nothing moving on that. So a couple of other fuses, CC and all of the requirement on it, DC and AC. So how many of you guys use fuses? Do you use fuses a lot? Yes. So this should be your baby for specification and all the stuff. Will you have other babies?
Manufacturer specifies everything.
Okay, so there you go. Or manufacturers, but if you're in the specification business, that would be really cool. Couple of other fuses, J fuse, for example, this baby, amp rating up to 600 volt, that can be current limiting. Fuse, look at the interrupting rating, you can use in current limiting. And all this again, this is a DC rating for it and an AC rating, and a current limiting and the interrupting rating at both the AC and the DC level. Look at the AC level is lower than the DC level because you lose the inductive reactance in a DC. In a DC short circuit, you don't have any reactance, any impedance. You only have resistance. So a couple of amps again, different amps. I'm going to go RK1. RK1 is a notoriously famous current limiting fuses too. That can go from, look at the amp, 600 amp all the way to 600 volt capability, and also you can use it at 240 level here on the current limiting. RK. So FRN, these are dual element time delay fuses. These guys, RK5 guys, notoriously famous with, they can use them with circuit as a backup overload protection for your motor, because they can give you 10 seconds minimum at 500 rated current. What would that be? Do you guys remember what Jeff Geljic talked about yesterday about the overload will give you 10 seconds or 20 seconds overload, right? For 600 amp. So these will give you almost backup. This will back up your overload for motors. Will give you a motor overload protection backup. So a couple of others, and I believe L is a feeder. It also can be time delay. It can be 5 seconds delay up to this. That would be time delay. You could use it on the motors too. So anyway, so all these fuses, guys, tons of fuses will get you what you want. Any comments, guys? Any questions about fuses? Comments, questions? For the sake of your time, I would like you guys to, I'm not done, but I would like you to sign this sheet. I would like you to please fill the evaluation for Mr. Coach tonight. Please pass that one. And how many of you guys are from other states? Anybody has a license in other states other than Minnesota? Okay, so if you have in other states other than Minnesota, please sign this sheet. So make sure you pass it around. Take it from my friend. And when you're done with these, also I want you to take your certificate. Take your certificate from here. Okay? Make sure they go around there. Pass them around, guys. Okay, any comments, guys? Any questions? Any comments? Any questions? Because of this, so I'm going to move a little bit with the circuit breakers, talk about indicating types. So circuit breakers have to be on and off. Off is always on. Circuit breakers, these are a few things about circuit breakers. Circuit breakers, if other than 500, they have to have a label on them. Marking, if you are using them as switches, they have to be labeled, shall be marked as SWD or NHID if you're using them as switches. Voltage marking, breaker shall be marked with a voltage rating not less than the nominal system voltage. If you have a voltage, guys, that rated 24120, can you put them in a delta system? That's another application for circuit breakers. If your circuit breaker says 24120, you can't install the circuit breaker in a delta corner grounded or ungrounded circuit, because if you ground the delta, the voltage to ground would be what? 240. And if you have a 24120, the voltage to ground in the circuit breaker is what? 120. So you exceed the voltage to ground rating of the circuit breaker. So that's a major thing when it comes to circuit breakers. Series rated circuit breakers, the smarter than Chad years ago decided, if you have a short circuit right here, 21K, and these circuit breakers are rated for 10K, that big boy that feeds this panel is 225 amp, it's rated for 225.22.5K. If these two, if the circuit breakers here and here are series rated, if this, now look at that, 25,000 is substantially more than what this circuit breaker is rated for. The way what the manufacturers do, guys, they coordinate it in a way where if that 10K sees 25, instead of trying to interrupt it, it will freeze. It wouldn't do anything. It will stop and wait for the main to clear the fault. It will wait for the main to clear the fault. So it has to be coordinated by the manufacturers to work together. It makes a lot of sense on up to 225 amp panel, lighting panels and receptacle panels and very small equipment panels. If you have MCCs or power panels, we don't use it. We don't use that series rated. Notoriously famous on lighting panel, receptacle panel, and small equipment panels. So that's series rated. It has to be labeled with series rated. So if you are to go take this QO circuit breaker and install another circuit breaker that fits there, that might compromise the integrity of your protection. Compromise the integrity of your protection. So series rated, combination. You can also in the field, selected under engineering supervision, in the field you can for existing building, you can series rate certain equipment. Combination series rated, engaged in the design and the maintenance of, this is the qualified engineer that you have to do this calculation in order to qualify this system as a series rated between this circuit breaker and these. So for existing system, you can series rate them in the field. Instantaneous trip. Like I said, everybody knows series rated ones. Why do we use series? There are two types of systems, guys. There are fully rated circuit breakers. We use them in power, switch gear, switchboard, and so forth. And the series rated, we use them in receptacle panels and lighting panels. The reason why we have series rated because the equipment is cheap. When you have a 30 amp circuit breaker rated for 10K, say this circuit breaker was $100. If it's rated for 225 amp, 225,000 volt, that will double or triple the price of this circuit breaker, because it has to be more robust to handle more short circuit. Okay, non-instantaneous circuit breakers in 2011, guys. If you have a circuit breaker in your building, like you guys have a Target and elsewhere, where the instantaneous are disabled in a drought circuit breakers, If you have a drought circuit breakers and you disable the instantaneous, you cut that instantaneous at the bottom, then you have to have, for protection purposes, you have to have one of the following: selective zone selective interlocking, differential relays, energy reduction maintenance switch with local status indicator. That's a little device. When you are to work on this equipment, if you rack that circuit breaker out or rack it in, you work on the energized, what you can do is on the face of the circuit breaker, you can tweak and turn on the instantaneous, which compromise the integrity of your overcurrent protection coordination. Now, if you have a short circuit, they're not going to coordinate. Who cares? We're working on it. It's just a transient. Turn it down. So now I put my energy reduction. So I put my suit and I can work on the energized. After I'm done, you turn it up again and leave. That's your energy reduction maintenance switch. One way, differential relays, I don't know if you guys use differential relays. They look at what comes into the switch gear, what comes out of the switch gear. They measure the current in and out. If there's substantial difference, they instantaneously trip. This means inside that switch gear, there is a major short circuit condition. And zone selective interlocking, they make the circuit breakers ahead talk to the circuit breakers downstream. They're communicating with each other. And if there's a short circuit high enough, they will trip and isolate with the zone selective interlocking, trip and isolate that short circuit. So what they want you to do with this game in 2011, they don't want you to have an instantaneous disabled without having other means of providing protection for your building. Because you disable the instantaneous, you will burn yourself if you're working on a 4,000 amp switchgear, or if your switchgear is not rated for disabling instantaneous, you will burn that switchgear or switchboard or panel board. Guaranteed. So that what came. Here's what we talk about. I showed you guys. This is the instantaneous that if you disable, you have to have an indicator that indicates maintenance mode. You can set it in the maintenance mode when you work on it. Any comments, guys? Any questions? Comments, questions? Did they put you to sleep yet? We're here for 6 o'clock, guys, or what? No? Now you wake up. We talk about conductors overload. Okay, the last thing I want to go, guys, over is fault current. If you need these, I will send them to your way, but I'm going to go directly into the fault current. Let's go to fault current 3-phase because that's the best way to go. Okay. No, Chad. Let's go directly into. Okay, here you go. Okay, so 240 line to line voltage on the transformer. Okay, single phase. That's the only way I can have it. Okay. Okay, I thought I have 3-phase. What happened? Did you guys steal my 3-phase one? Okay. No. I was just gonna go over that quick for a second, if you guys don't mind. Get you. I know you're eager to leave, and I understand. Okay, let's go directly into the ground fault. There you go. Okay. See how fast we can go? Okay, ground fault. Short circuit, let's go to the 240 right away. Okay, when you do short circuit calculation, guys, by hand, oh, I know where it is. That's why. Okay, let's go directly to single phase. Here you go, 3-phase. Here's the document that we should have given you. This document will give you how to calculate short circuit on equipment. I'm going to take you guys directly into the steps right in here. So the first step that you have to do, if you have a transformer here, the reason why we guys do a short circuit calculation, because in 2011, the NEC code book started requiring you to label your service in other than dwelling with the available short circuit. Now, if your system is an engineered project, like a lot of them are, it will come with the engineers. If it's not, online, Busman and a couple of other guys had a little calculator that you can stick a couple of numbers and give you the short circuit. How to do it by hand? These are directly from Busman, guys. You take the full load current of your transformer. If you look at step 1, you know how to find the full load current of a transformer. Take the kVA divided by the voltage and the modifier of the three-phase. This is an 1804 amp transformer. Divide the transformer by the impedance, give you the multiplier. That's 3.5 is the impedance of the transformer. Then multiply this multiplier by the full load current. Then at the secondary of this transformer, right in here, guys, if I am to take phase A, phase B, phase C, tie them together, flip the switch, you will be encountering, what is it, 56 or 61? 61.5 thousand amp. That's how we do the calculation at the secondary. Now, because I have a can you see that motor here, sitting here? Motors momentarily, upon the short circuit condition, they will turn immediately into a generators and they start pumping current into your building. The current that they're going to pump is equivalent to their close, in this case, 4 times their full load current. So I have a motor here and my motor right here, and the full load current of this motor happened to be 1804. So 4 times that motor, it's going to give me this amount contribution from my motors. Then you add the contribution of your motor to the 51, not 61, the 51 of your transformer. That will give you a total transformer coming from the utility and coming from your motors contribution of 58.7 kiloamp. So that's the label that you're supposed to stamp. That's the label that you're supposed to stamp your equipment right here at this value. Any comments, guys? Any questions about sizing it? Yes, sir.
What if that panel has like 30 motors coming out of it?
Then you're going to take the full load of every motor, multiply it by, here we use 4 to 6, use the inrush, basically it's the inrush. 6 times the full load current of every motor, add them up, then add them to this value. Take the full load current of every motor, multiply it by, here we're doing 4, but 4 to 6 is a good approximation. So that's right here. Now then, that's at the secondary side of a transformer. But I took 25 feet, guys. I pulled cables from here to here, 25 feet, 500 kcm, 6 runs it looks like, and I brought it to the switch here. So to accommodate for the impedance of the cables, right? The cables have an impedance. To accommodate for the impedance of the cables, you have to do this math. So you take this, here's the available short circuit. This is how many runs. This is the circular mill. This is a 480. So you got your multiplier. That gets you the impedance contribution of your cables. Then this is called the F factor. Divide the F, find the M factor, which is do this math, and then multiply it by the available short circuit, and that will get you the value that will be, the current coming in will be knocked down because of the impedance of the short circuit. So that 49 will be right here. Add to it the motor value, and that total at this point here will be 57.0. 57.0 right at this point. Contribution from the motor and choking from the cables. So that's how you do this calculation. 25 is the feet. This is a short circuit. 22165, this is the C factor. They call it the C factor for the cable. And there's a lot of tables, guys, that can get you this calculation. Now, when you go to step 2 here, right here, so then you're going to take the value here and start doing calculation based on the impedance. We have one cable. Here's the C factor for this cable. Here's how far it goes. Available short circuit, the voltage. This will be your factor, F factor. Divide it to find the M factor. F factor is F for funding. Divide it to find the M factor. And from the M factor, you multiply it by the short circuit right at this point, not here. That will give you the and the contribution of the motors. That will give you the contribution at this point. So right at this point, look at that. We knocked down the short circuit, guys. From starting, we started with 58. Because of the impedance, we knocked it down to 42, just by the impedance of the cables. just one impedance by cables. Any comments, guys? Any questions? Comments, questions about that? So that's how to do calculation by hand. Now all these F factor and C factor and all this good stuff is coming from a bunch of tables. The second one, so here's, I don't know if we have that table here. Okay, so the tables that you find the F and all these factors are coming from, they're all in color. Here you go. So we have the C factor. You can see here's a 500 conductor. If I have 3 conductor in a conduit in a steel, that's where 22185, that's the contribution, the impedance contribution for 500 conductor is this value based on 3-phase conduit steel. And they go through the different type of conduits. Of course, copper, aluminum is down here. All these values, guys, are published right in here. All your values are published right in here. So, any comments, guys? Any questions? How to calculate the short circuit value? Do what? In my fancy calculator, no. But anybody has, let me just show you how easy if you don't want to do that. Here's the short circuit that we use. Here's my riser. When you run the short circuit calculation, guide is as easy as running balanced loads. I need a short circuit right here, and you run your short circuit. I have multiple things, and you got yourself a short circuit for the whole system. So then you get to your report text. I need my short circuit report. Just show you quick here. That's how you get them from the engineering firms. And you go all the way and to the bottom, and this is the available short circuit fault summary. So here's the fault. See how easy at every bus, my 3-phase, my XR, it's a big deal, and my ground fault. So at this bus, I could have named them differently, guys, and get a meaningful more numbers. So this is a 30. Look at the voltage ground fault. It's lower, typically lower. And all the way to at the generator, I have a gen bus. At the gen bus, because of contribution from the gen, I pumped up to almost 60K. 60K. See how easy that is when you model the system? Any comments, guys? Any questions? So that's how you do the short circuit calculation if you have a software. There's a lot of calculators in the industry that you can go and use to calculate your short circuit. So that's, what else? Before I let you guys go, I have 10 minutes. I think I have 10 minutes. Any comments, guys? Any questions about that? I'm going to put, feel free to drop me an email if I can be of any help. Let me see if I can. Can you guys pass the eval if you don't mind, guys? If you can, I can pass these papers. Let me just take here a second and type my email. Okay, here it goes. Here's my email. ckurdy@dunwoody.edu. Okay, and then here you go. So here's my email. Feel free to drop me an email if I can be of any help. I will make sure before you guys leave that each and every one of you, did you guys sign all the sheets? Sign the sheets? Yeah, the evaluation sheets, anybody else? Is that your eval? Did you guys pass it? Okay. Did you guys pass the eval? Did you guys sign the sheets? The first day and the second day? Okay, so that's important. Did you guys get all, okay. Did you guys sign for the other states? All of you signed for the other states? Okay, if you need to. Each and every one of you should have signed twice today, right? Twice? Okay, good. The last thing is, did you guys happen to get your certificates too? Cool. The last thing I would, grab certificate. I'm glad you guys do the evaluation. Everybody has it down. Can I get your book?
On the certificates,
1, 2, 3, yes, sir.
got a different license number from a different state. This one has a Minnesota license, so I need another one with my license number after state.
Oh, one, like, okay. Can you email the office or you still write directly and note and I'll call them now. Okay. Yeah, that should be able to get you. Alright, so here goes. Thank you. Well, thank you, Trace. I hope we contributed to your knowledge a little bit. Please take a few seconds to evaluate the class for both Mr. Kiljic and I, and tell us if we should stay in this business or move somewhere else to a different business. Thank you again. Is it?
So it says I'm like at 8 credits. I've been here for 2 days.
Does all your say 8 credits, guys? Say 16. Can you email the office or I can send get you anyone if you want. Just say 16 on that. Your name is in there, right? I can do it.
Yeah. Name's on it, everything else.
Say 16. If we're receiving it. 16. Okay, we'll get you a new one. Okay. Thank you, guys. Make sure you signed in.